Yes.
Good morning.
Good morning, sir. Good morning.
Namaskar, namaskar.
Should we start, sir? People are still joining.
Please go ahead.
Yeah. Thank you, sir. Raju Sinhaji.
Sir. Respected Chairman DCC and Secretary Telecom, Sri K. Rajaraman, sir. Respected Professor K. Tyagarajan, HOD Department of Physics, Bennett University. Respected DG Telecom, Sri Haksa. Respected Member Services, Sri A.K. Mittal, sir. Respected DG NTI Prit, Sri U.K. Srivastava, sir. Eminent learned speakers in the session, Sri Shivarajan, City of Teja Networks, Atul Kumar Gupta ji, C. Sri Anjani Kumar Vaish from Siena, Sri Nitiraj Shekhawat ji from Infinera, senior officers and colleagues from DOT headquarters, LSAs, TEC, BBNL, MTNL, BSNL, and other units, researchers, academicians, startups, students from technical institution and applied sciences, fellow colleagues from NTI Prit, ladies and gentlemen. Very good morning to all of you. On behalf of NTI Prit, I, Raju Sinha, DDG Transmission and Next Generation Switching, welcome you all. We assembled this forenoon in the National Workshop on Advanced Optical Communications. The workshop has 3 sessions: inaugural, that we are currently in, technical session, and then question-answer sessions. May I now request our DG NTI Prit head, Sri U.K. Srivastava, sir, for his welcome address. Over to you, sir.
Thank you very much, Mr. Sinha. Good morning, ladies and gentlemen. At the outset, I extend a very warm welcome to our Secretary, Telecom, and Chairman DCC, Sri K. Rajan, sir, who has kindly agreed to inaugurate this webinar on advanced optical communications. The Secretary is very keen that the latest developments in the field of optical communications is discussed and debated in the country, and we should have a measure of what is our existing capability and what needs to be done in different time frames. Accordingly, in fact, an expert committee has been set up to work out details. I welcome you once again, sir, to this event. I will also extend warm welcome to Sri A.K. Mittal, a member of DCC, and Sri Nizamul Haq, DG Telecom, to this event. Their presence today is very encouraging to all of us. And special welcome to Professor K. Tyagarajan, who is the co-chair of expert committee I just mentioned about. The good professor has kindly agreed to deliver the keynote address in this event. In fact, many of the members of the expert committee, they are all chelas of Professor. Welcome, sir. I further welcome the eminent speakers today, including Dr. Kumar Sivarajan, who is also a co-chair and very experienced industry stalwart. There are also experts from CDOT, Siena, and Infinera. I extend very warm welcome to them all. I also welcome the officers from CDOT, TEC, LSA units, DOT headquarters, academia, and industry for their participation this morning. Today, we have started the program a bit early, therefore, people are still joining. But anyway, those who have joined, most welcome. Ladies and gentlemen, all of us know that the introduction of 5G services in our network is around the corner. The 5G GNBs will require massive amount of backhauling, for which optical fiber systems are the best option. And as these systems will be deployed in various networking configurations, a large amount of networking equipment shall also be required to be deployed. Since the internet has taken over a major percentage of the world's communication system of the present times, it is safe to say that future of optical communication is bright enough. Several giant end user industries are pushing the market to grow at a remarkable speed. And the improvement in fiber optic technology, networking solutions, surveillance, and telecommunications, etc., are great opportunity points for the future of optical communication market. Optical communication and networking market size, in fact, was valued at $18 billion in 2020, and it is expected to grow at a CAGR of over 5% between 21 and 27. Therefore, by 2027, the market size will be around $30 billion. The rising development of new innovation technologies such as IoT and artificial intelligence, they are enabling the need for faster internet communication standards. Keeping the market size and importance of this technology in view, we have structured this webinar. This is the first part of the webinar wherein we are focusing on the optical systems. The next part of the webinar, which will be conducted in a couple of weeks' time, wherein we shall focus on the development of other technologies like Li-Fi, free space optics, quantum key distribution, and many other related developments that are taking place in our IITs and startups. In fact, I have got a couple of requests for participation for presentation in the next webinar, which I will certainly do and oblige those industry members. So ladies and gentlemen, these are very exciting times for us all when the government has total focus on development of indigenous technologies and Atmanirbhar Bharat. I'm sure that this event will provide a way forward for further discussion in this area. I once again welcome you all. Thank you very much. Back to Mr. Sinha.
Thank you, sir. We'll soon be organizing the second part of the workshop. It's a matter of pride that Professor Tyagarajan, HOD Department of Physics, Benetton City, is with us today. It gives pleasure to have Sir today and make us feel that we will keep learning and make as a feel of a student. Many of our colleagues at NTI PREET and other places have been student of yours, sir. Professor Tyagarajan was superannuated from IIT Delhi in March 17, and as we know, he is currently professor and head of Department of Physics in the School of Engineering and Applied Sciences at Benetton City. He has held visiting positions at various institutions in France, USA, Canada, Hong Kong, and Japan. He has published more than 160 research papers in the area of optics and photonics in international journals. He is a co-chair of the Task Force of Advanced Optical Communication of DOT. I now welcome Professor Tyagarajan for his keynote address. Over to you, sir.
Thank you, Mr. Sinha. Thank you very much. A very good morning to all of you. I would like to thank the committee for having invited me to give a talk here in this workshop. I will share my slides now. One second. Can you see my slides?
Yes, sir.
Yeah, okay. So I will just briefly go through what I feel is some of the important developments that are taking place in optical communications. I will not talk in terms of networking. I will not talk of the other kinds of technologies which are used, but I'm primarily looking at the transmission itself of optical signals. So just to recall, light wave frequencies are very, very high, million times those of microwaves, and hence have enormous information carrying capacity. And that's the reason why light wave communications took over and is the primary mode of communication today across the globe. And the entire globe is now connected through this single mode optical fibers. Let me close this window here. Yeah, sorry. Through optical communication system. Okay. So the communication is primarily through single mode optical fibers, which are made of silica glass. Typically dimensions, outer dimensions about 125 micrometers, and the inner core diameter is about 10 to 50 microns. And virtually all communication technology today is based on optical fibers. The operating bands that are primarily being used today are the conventional band C band, 1535 to 1565, and then we have the long wavelength band, right up to 1630 or so. And then we have on the other side, you have one side the short wavelength band, less than 1535, and the L plus band, which is beyond 1635. So as you can see, the attenuation of standard optical fibers is below about 1/4 dB per kilometer in this entire band of SCLL+. So in principle, it is possible for us to use the entire band of communication over this entire band for communicating our signals. So a 1/4 dB per kilometer essentially implies that for 80 kilometers, you have about 1% of the signal still left in the optical fiber. We are all aware that the internet traffic is exploding, and the capacity of the currently laid optical fiber communication systems is actually reaching its limits. There has been 4 orders of magnitude increase in information carrying capacity of the network in the last 3 decades. And as you increase the input power into these optical fibers, you are facing nonlinear optical effects, which will finally limit the capacities of these systems. So the capacity increase has been met by multiplexing, various multiplexing technologies using wavelength, division multiplexing, polarization multiplexing, amplitude and phase of the optical signals. So the core networks may need to operate in the petabits per second regime by about 2030, which is 1000 terabits per second. That's the expectation, which essentially implies that we need to develop new techniques to achieve this extremely enormous increase in capacity that is expected. So this is just a figure which shows that optical fibers actually carry, a single mode optical fiber carries 2 orthogonal polarization states. So you can actually multiplex these 2 polarization, the vertical and horizontal, independently of 2 signals. You have wavelength division multiplexing. So you can have multiple wavelengths at different, in the low loss region of the optical fiber, each wavelength carrying its own communication channel. You can use phase multiplexing, phase division, QPSK, for example, or you can use both amplitude and phase in the QAM systems where you have both amplitude and phase. So these are all coherent communication systems and need extremely good lasers and signal processing capabilities to use all these abilities. Now, using all this, we have sort of used up all these kinds of freedoms that we have, but we now need to increase the capacity beyond this point. So if you look at a single mode optical fiber, you have the what is called the fundamental mode of propagation. And the fundamental mode actually supports 2 orthogonal states, one horizontal and vertical, for example. These are called LPU modes. And so what is one of the techniques is to use these 2 as 2 different channels of communication between the 2 ends of the communication link. So if you go to higher order modes, for example, if you take fibers which support more modes by either increasing the radius of the core of the optical fiber or increase the index difference, then the fiber starts to support more modes. So for example, if you have a fiber which is slightly higher diameter fiber, core diameter fiber, you have the 2 LP modes, the fundamental modes, 2 orthogonal polarization, and you also have 4 different modes that can propagate in the fiber. These modes are like oscillating fields of a oscillating string, for example. So these are modes which have the pattern like this, modal distribution like this, which is the cosine distribution. There's the sine distribution, 2 orthogonal polarization states. So actually, if you take a fiber which carries the LP01 and LP11 modes, it actually supports 6 modes. So you can actually use, just like you have 2 different polarization states, you can use all these 6 modes as 6 different channels through a single fiber, and hence multiplex this communication ability. So this is a figure which I picked up from NTT Technical Review. As you can see here, this horizontal line here, the red line, is the physical limit of single mode optical fibers at about 100 terabits per second. The nonlinear effects become very significant around this number. So if you want to overcome this, you have to go to what is called today as space division multiplexing. And these are some results that have come out of space division multiplexing, where you're talking about 1 petabit per second communication systems. So beyond this point, we are actually forced to employ different techniques, to evolve new techniques so that we can increase the bandwidth further of fibers. So to have the space division multiplexing, there are different solutions that are being looked at currently across the globe. One is to have a fiber with multiple cores. You can have these cores which are significantly separated apart so that there is no crosstalk between the cores. Please remember that to be consistent with existing technology, the outer diameter of the fiber will still need to be 125 micron. So the diameter of this fiber, outer diameter, is fixed, which means that we can only fix a certain number of cores within it. So this is one way, which is weakly interacting cores. You can have more cores in the fiber, but then the problem arises that these cores start to interact with each other. Light gets coupled from one to the other, and you have mode mixing that is taking place. Or you can take a fiber, a single fiber with a larger diameter, which becomes a multimode fiber, and it supports multiple modes. And all these solutions are actually possible and being investigated today. So each core of the multi-core fiber can carry independent signals, and each of those signals can be multiplexed using WDM or polarization multiplexing, quadrature phase shift keying, etc. So you can actually, current technology gets multiplied by the number of modes that you are using in communication systems. So using these kinds of techniques, these are some recent results, up to 10.66 petabit per second transmission over a 38 core 3-mode fiber over a distance of 13 kilometers. And you see here a petabit per second, and the number of WDM SDM data channels is 11,640 using the C and L band. So this is a significant increase in capacity that you can achieve using this space division multiplexing. So there is a lot of work going on currently in the worldwide. How do you reduce mode mixing among the modes so that you can keep them independent? You have to develop components for multiplexing, demultiplexing of these SDM channels, optical amplifiers for the multiple modes that are propagating through these channels. How do I design new optical fibers for reducing mode mixing among these various modes? What are the effects, nonlinear impairment effects that are taking place in these signals? And there's also a lot of work going on in a different kind of modes that are being used, which is called optical angular momentum modes for reducing mixing. So I feel that space division multiplexing will be an extremely useful in new fiber deployments, especially connecting data centers. This possesses significant opportunity in this area for developing novel solutions with possibility of patenting in the country. A concerted effort may be initiated in this area so that we are prepared for the bandwidth explosion. And fortunately, we have in the country a couple of places where fiber fabrication facilities exist. Sterlite Aurangabad does fiber fabrication and supply. Central Glass and Ceramic Research Institute, which is a CSIR lab in Kolkata, has a very good fiber fabrication facilities, and there may be more. And so if we have an interaction between academic institutions, R&D institutes, and industries, I think this will be a very productive area for us to put our efforts in. So as you can see here, this is another figure which I picked up, a technology roadmap. We're talking about 1 etabit per second kilometer per kilometer, 12 core fiber. So all the increases that are taking place today seem to be using space division multiplexing technologies. That's one area. The other area which I feel could be very important for our future is free space optical communication or Li-Fi. And whenever you need to have very high bandwidth line of sight communication over short distances, say between data centers or buildings or terrestrial last mile connectivity, connecting across rivers, etc., then you might need to use this free space optical communication where you're not using an optical fiber, but using the free space for sending optical signals. And there is a feeling that this may play a very important role in the future 6G era, as well as in quantum communication information networks, which will pave the way for global quantum internet. And of course, satellite communications, satellite ground communication can take place using free space optical communication systems. And here, there seems to be some interesting work across the globe, where instead of the standard modes, people tend to use different sets of modes here. These are some patterns of modal patterns which are called optical angular momentum modes. The significant advantage of this is there is less mode mixing taking place, and you can actually multiplex. And these kinds of modes can be used in underwater communications. So we will need specially designed and optimized components such as lasers, receivers, etc., to be designed and developed. And of course, in free space optics, we have this problem of turbulence, beam divergence, beam pointing, etc., which needs to be resolved. So there is a lot of effort going on across the globe, and I'm sure in India also there are places where FSO activity is currently on to achieve increased free space communication activities. The last one, which I would like to mention briefly, is quantum communications. Current technology uses classical systems, and there's always a problem of security. And it is known that using quantum physics, if you develop quantum communication systems, you can have extremely secure. In fact, according to the laws of physics, it's completely secure. Of course, you will never have a perfect system. So there are a lot of work going on how to make it more secure. And of course, there are hackers who are trying to see how we can hack quantum systems. So I feel that this is going to play a very significant role in secure communications in the future, and is one of the best disruptive technologies that's coming up, and it's at development stage. There has been many practical implementations. Here is, for example, a 12-mode quantum photonic processor, which is just like an integrated electronic circuit. You have an integrated optical circuit here, which has electrical inputs, and you can control the quantum nature of light in this kinds of circuits. We're all aware that in India, there's a lot of work going on. CDOT has recently demonstrated one, ISRO has demonstrated, DRDO has demonstrated, with PRL, ISRO has demonstrated. There's a lot of work going on at Raman Research Institute, Bangalore, ISER Pune, and some IITs are putting in strong effort. And this is also a trust area of the Department of Science and Technology. They have opened a quantum technology hub at ISER Pune. And I feel that if we further support R&D activities in this area with focused objectives involving multiple organizations within the country, we may be able to speed up the activities and target implementation of the technology for real-world applications. And this one actually gives us immense opportunities for carrying out innovative work, because this is not fully developed. There's a lot of open space available for the country. Integrated optics platforms, which will finally be a part of the quantum network, need to be developed. There are groups in the country who work on integrated optics. They may be supported and maybe looked at target-oriented research. Because this is a very fast evolving field, a coordinated effort will be needed to progress at a rapid pace and to be able to compete internationally. Incidentally, I just noticed yesterday that this year 2022 is the International Year of Glass. Just like we had the International Year of Light, we have the International Year of Glass. The United Nations has declared, General Assembly has declared this year as International Year of Glass. And glass is so important in our communication systems that we sort of welcome this designation of this year as the International Year of Glass. So let me summarize. Expanding requirements of bandwidth needs new and innovative technologies in the country. A number of academic institutes, R&D organizations, and industries are actively working in the area of optical communications. A proactive effort to initiate target-oriented R&D and implementation of ideas that will shape the future will help the country in moving ahead. In order to be impactful, manpower at specific scientific and technical levels needs to be cultivated within the country. Because once you expand, you need a lot of manpower, and academic institutes may proactively introduce courses at the undergraduate level to generate required skill sets. Thank you very much for your patient listening. Thank you.
Thank you very much, sir, for your address and wonderful thoughts on the matter.
Thank you.
The artery of optical communication, optical fiber, with the raw material as glass has been declared as International Glass Year. You have also touched upon the activities on FSO quantum communications, which gives immense opportunity for researchers, industry, and academia to work upon to reach towards advanced optical communication and higher speed as desired by humankind. Thank you, sir. We at NTI extremely delighted and privileged to have Secretary Telecom and Chairman DCC who has accepted our invitation to inaugurate the workshop. Thank you, sir, and welcome you again. Sir, need no introduction, but all the participants who have joined the workshop. Sri K. Rajaraman is an Indian Administrative Service Officer from 1989 batch. He was previously working as Additional Secretary in Department of Economic Affairs, DEA. He has worked towards fostering economic relations worldwide, particularly G20 and BRICS countries. He holds a bachelor degree in engineering and master degree in financial management. May I now request Secretary Sir for his inaugural address and to declare the workshop open. Over to you, sir.
Thank you, and first of all, a very good morning to all the distinguished panelists on this timely conference that you have organized, and I think which would discuss substantive issues on the advances in the field of optical communications. I would like to first of all thank Professor Tyagarajan and his team for having and other members, including Dr. Sivarajan and others, for being part of the optical communications task force, which actually is discussing very, very substantive issues on how to take this country forward in terms of getting into advanced optical communication technologies that can be built within this country. So and also exported out of this country. So I would like to first of all place my sincere appreciation to the entire team of this who are members of the task force. I would also like to thank DG NTI PRIT, Mr. Srivastava, who has been very active in getting to organize a lot of these cutting edge technology roundtables, which dwell on issues which are the subject matters of the market tomorrow. So these are extremely strategic issues, and I'm very thankful to the NTI PRIT team headed by him in organizing such very, very timely conferences. I only hope that these conferences are followed by much more intense roundtables where technologists actually sit together and try and develop a roadmap, both in terms of policy as well as in terms of R&D and so on and so forth. So, I mean, all of us are aware that the Honorable Prime Minister and the Honorable Finance Minister have all, in the last couple of years, laid out a number of policies which focus on technology development within the country. In May of 2020, the Honorable Prime Minister announced the Atmanirbhar Bharat movement, which essentially focuses on becoming self-reliant on various aspects of technology. Today, thanks to the efforts of various stakeholders, including market players like Tejas Networks and so on and so forth, we have a substantial amount of strength in optical communications. And agencies like CDOT and research institutions in IITs and other places, all of them have played a very important role in development of these technologies. So I'm very, very thankful to them. But a lot of ground has still to be covered. So we need to actually look at the massive requirements of digital communications within the country while focusing on technological development. So if we are able to look at the outcome indicators, for instance, I think the bandwidth that is delivered to the villages, or the overall capacity in terms of GBPS which is available to any rural area, and I'm sure that there is a lot of ground to be covered. And I think this would be covered by affordable technologies which are not expensive, but at the same time very robust and resilient. So therefore, there is a need for a country like a developing country like India to focus on such kind of technologies which draw inspiration from advanced technologies, but actually adapt it for use within such very large and very diverse country like India. So we have a tremendous potential now because of convergence of a lot of these technologies. Today we have 6G, which talks about a lot of a vision of convergence. Convergence between terrestrial networks and space networks, convergence between mobile, wireless and wired networks, and so on and so forth. There a tremendous amount of convergence is going to happen. Similarly, I think the way in which these systems interact with the human beings is also undergoing tremendous transformation with the availability of new forms of human-machine interaction. So therefore, keeping in mind all of these, and also the fact that the way in which certain policies are requiring higher productivity, higher turnaround, higher efficiency, etc., are driving the market towards use of such of these technologies, including, say, Internet of Things, big data, machine-to-machine communications, and so on and so forth. So I'm sure that with the spread of use of these advanced technologies, the need for bandwidth and the need for higher resilience and reliability of networks is going to take a very, very important turn. So not only that, from a national security perspective as well, I think there is a lot of importance given to the resilience of these networks against any significant event like a war or some such thing. So from that perspective, optical communications will play a very important role. It has got a very strategic role in ensuring that the digital communication of the country is fairly resilient to all these forms of attacks and so on and so forth. So therefore, from that perspective, optical communication is a very, very strategically important sector, and therefore, and from a market perspective, when we see an explosion in the use of bandwidth because of the growth in over-the-top communications, video communications, entertainment, and so on and so forth. Video conferencing, work from home, etc., etc. So the need for bandwidth has actually exploded in recent times, and I am sure that it is only optical communication which can deliver such kind of bandwidths that we are looking forward of this scale. So now we have a very important network called the BharatNet, which has a great vision. A lot of work has been done, but a lot more work has to be done to actually put it to effective use. So I would request the technological leaders here under Professor Tyagarajan and others to actually brainstorm and give us a lot of input on how BharatNet has to be reconfigured or led or steered to lead us to a high quality communication facilities in the rural areas. So we have a constantly evolving strategy, but nevertheless, I think we would benefit from the expertise and the experience of the participants in this thing in this workshop. So we would like to hear from you. Similarly, I think if you look at the work which needs to be done, I would like to say that as Professor Tyagarajan has mentioned, there are a large number of stakeholders already who are working in silos within the country. I think that is very unfortunate. I think so. In today's world, collaboration is a mantra. So unless all of us get together, I think then it is going to be each of us reinventing the wheel at a great price, which is actually economically inefficient and also inefficient in the form of a time perspective. Because I think together, I think we can do it faster, cheaper, and maybe better. Maybe because more souls can actually add a lot more wisdom. So therefore, I would request that the optical communication task force that has been set up should actually branch off into sub-task forces and try and see how other collaborators can be brought on board. And I think Professor Tyagarajan was talking about CGCRI, ISER Pune, and so on and so forth. I think we should bring all these kind of stakeholders into highly specialized sub-task forces so that each of them can work together, and finally we have a coherent whole which emerges, which as the national policy and a blueprint for investment in R&D and manufacturing and so on and so forth. I would also request that the task force must become very active in terms of getting access to the latest in terms of technology, by organizing international technology conferences. We'll be very happy to support you in this process. I think we should have an annual advanced optical communications conference, which mirrors some of the conferences which happen in the West, I think in the US and others. So I would request that we must make a beginning and maybe NTI PRIT, with the help of the members of the task force, can actually take the lead in hosting this conferences on an annual basis. It should not be a one-off event. It should be part of a larger program with a much longer vision and a roadmap ahead. The other thing is that probably we should also look at the opening up a couple of test beds. And I think just like I would like to point out to the 5G test bed, which very successfully the IIT Madras, IIT Kanpur, Mumbai, Hyderabad, IISc Bangalore, Samir, and others have actually successfully put together. I think we today have a working 5G core and RAN and all the other components. I think so. Thanks to the test bed. So I'm sure that we should immediately, without loss of time, try to structure an optical communications test bed, which will look at materials, as Professor Tyagarajan has suggested, maybe advanced optical communications fiber materials, as well as in terms of systems. So I would request that maybe the task force should maybe in the next 1 or 2 months deliver a design of a test bed which will bring in the topmost of the players on this platform. And so essentially we are platformizing research, and on a joint development basis. So, and I would request that maybe we will be very happy to be part of the investment team to support and take this forward. So, incidentally, the Honorable Finance Minister during this budget has announced a 5% investment into the technologies that will support proliferation of broadband in rural and remote areas. And I think optical communication is the way forward. And therefore, I think we will look forward very avidly to the outcomes of the task force in terms of evolving a design of the test bed and also releasing a white paper for India in terms of what advanced optical communications technology development. I would also look at pilots, because recently we are actually in the process of finalizing pilots where I think we are supporting pilots in free space optics and so on and so forth under the USOF banner. So we would be happy to also pilot certain advanced optical communication trials of technologies which are developed locally in the rural settings and maybe even in the urban settings as well. So recently I was reading about how like for instance a test network like called CENIC, which is testing about a 34 Tbps link in California, on a C+L kind of a transmission link. So therefore I think we should have more of these. I think with Professor Tyagarajan talking about space division multiplexing and coherent optics and so on and so forth. I think there is an opportunity for us to pilot and test a lot of these technologies which are currently large scale. So we would be very happy to pilot these and take it forward. I think so. I would look forward to a lot of these things. So similarly, I think a lot of evolving technologies we keep reading about in the technical magazines, including things like say 800 gigabits per Ethernet. 400 ZR optics. There are so many such technologies which are in the cutting edge. So we would request that the task force should look at who are the parties who can probably be brought on board in kind of investing in such kind of research and how we can work together to enable its development. So essentially, while we work on research, I think what we need to do is, as I already mentioned, is to set up a very coherent Indian Optical Communications Alliance, which actually spans research and development, manufacturing sector, the research institutions like CDOT and CGCRI and so on and so forth, into a very tightly knit community which will work together, intensely collaborate, and focus on bringing out products in the market which can be global scale. So with these few words, I declare the conference open and hope that these conferences open up avenues for further action as will be proposed as part of the various discussions. I look forward avidly to the outcomes of this workshop and hope conference all success. Thank you very much. Jai Hind.
Thank you, sir.
Thank you.
We are very fortunate to listen to your inspiring address and thoughts, wherein you elaborated the importance of today's topic and its relevance and use of advanced technology. You have also stressed upon for industries, researchers to work in harmony and government support open up in that matter. Thank you so much, sir, for your gracious presence. Well, all participants, we have come to end of this inaugural session, which will be followed by technical session. First and foremost, I would like to thank Secretary Telecom, who despite his busy schedule has spared his time and joined the inaugural session. Secondly, I would like to thank Professor Tyagarajan for sparing his valuable time to attend the session and address the gathering. I would also like to thank our DG and Head NTI-PRIT, Srivastava sir, who has been great source of inspiration in formulating this workshop and always guides in making activities meaningful. Thank you all. Now we'll move to technical session of the workshop. I'll request Dr. Transmission Subhas, my colleague, to conduct and host the technical session. Over to you, Subhas.
Thank you, sir. First of all, I would like to invite the first speaker, Sri Shiv Kumar N. Rajan, sir. He is CTO Tejas Networks. He will be delivering a talk on DWDM, evolution, challenges, and future. Sri Shiv Kumar, sir, he is the CTO, Chief Technical Officer at Tejas Network. He has nearly 3 decades of experience in the field of telecommunication. He is fellow of Indian National Academy of Engineering. Sri Kumaran has co-authored the best-selling books titled Optical Networks, A Practical Perspective. He is also a recipient of the prestigious IEEE WRG Baker Prize Paper Award in 1997. Sri Kumaran was the first chairperson of the Governing Council of Telecommunication Standard Development Society India. Prior to joining Tejas, he was an associate professor at IISc Bengaluru and a research staff member at the IBM Thomas J. Watson Research Center, New York. He holds a BTech degree in electrical engineering, electronics from the IIT Madras and a Master of Science and PhD from California Institute of Technology, USA. So over to you, Mr. Sri Kumar and Sivarajan, sir. Please, sir, proceed.
Thank you. Thank you for the introduction. Is my screen visible?
Yes, sir. Yes, sir. Please go ahead, sir.
Okay, very good. Thank you. I thank Srivastava ji for the invitation. It's a pleasure to be here. Thanks for the nice introduction. I will pick up where Professor Tyagarajan left off. So if you weren't paying attention, that was a prerequisite. So for understanding this talk. Okay. So let me, I'll do a little bit of history, but I'll try not to repeat whatever Professor Tyagarajan said. So start with history, and then I'll of course end with the future and setting challenges. There is around 1960, many scientific breakthroughs happened which enabled optical communication. It's always like this, they were all independent, but somehow they all came together. So high-powered lasers came around 1960. WDM muxing was around 1958. Okay, fiber, that showing that fiber can transmit signals over long distances. This was shown around 1954. I think Narendra Kapani has been in the news recently. He passed away, and he wasn't recognized sufficiently for this. Anyway, he laid the foundation for optical fiber glass, and we still use glass. We maybe should be using different glass in the year of glass, but we'll come to that. And fiber, Corning developed fiber in the 1970s. But I would say the most significant development for communications was erbium doped fiber amplification, so that you could amplify light as light, without converting back to electrical signals. And this also happened around 1958. And the first erbium doped fiber was done, I think, in BT Labs, maybe around the late 80s. So everything came together in 1960s to lay the foundation. And in terms of commercial systems, it took 20, 30 years. So the first commercial WDM systems only showed up in the early 90s. I was actually lucky to be involved in our IBM Watson Research Center when we were building almost the first WDM systems in industry. And I think that was probably the first WDM system that was deployed in Wall Street in 94, 95. So as part of that, I was doing theory and publishing papers. But in my lab, I had people tinkering with fiber. They actually got IBM wrote fiber from BT Labs in an envelope, and they got lasers from IBM Zurich lab, pump lasers, and they're trying to build all this. So I was there, and we progressed from 10 gig to 800 gig systems today. Okay, I think we started with a couple of lambdas, 40 lambdas. I think were there by the late 90s, and today we can do 300 lambdas. 320, but we cheat, and I'll tell you why we cheat. We can't go very far with so many lambdas. Distances, I disregard any WDM communication system that doesn't achieve 1,000 kilometers. I think 1,000 kilometers is kind of a minimum to do long haul. So I disregard the experiments which show 13 kilometers and 23 kilometers, and I'll come to that. But we can today go, without regeneration, 39,000 kilometers. That's the circumference of the Earth. So you can go on the longest path from any 2 points on the globe, and you don't need to regenerate. Amplifier technology has seen almost no advances. EDFAs were there in the late 90s, late 80s, early 90s. Then Raman amplifiers, it's named after our own C.V. Raman, though you won't know it when people say Raman all the time, right? So, and that came in the late 90s. And since then, nothing, blank. Okay. And Coherent has played a big part in 100 gig. So 100 gig transmission systems wouldn't have been possible without Coherent. Professor Thiagarajan already introduced polarization to you. Well, of course, polarization is a fundamental optical concept. In the 90s, when they were doing optical communication, they were not using polarization as one of the multiplexing modes. Neither was amplitude or phase used. It's only WDM, and you just turn the laser on and off, and it was actually called on-off keying. Whereas, wireless communications, especially in RF, microwave and so on, were already using polarization multiplexing extensively. Also, Coherent was widespread in RF communication. Microwave transmission systems used both polarization communication, polarization multiplexing, and Coherent transmission. In fact, Coherent receiver is sort of the foundation of how RF works. By the way, the cellular networks today transmit two signals to you, one at horizontal polarized and one vertically polarized. So this is very, very prevalent in RF. And in the last 15, 20 years, optical fiber communications have also borrowed polarization communication, polarization muxing, as well as Coherent technology from RF. And polarization immediately doubles the capacity. Coherent does a lot more. So first, thinking in around 2008, Coherent optical systems were deployed. The number of photons per bit you need to detect a bit is, this should be a bit, okay, not but, is almost at the theoretical limit. It's just a handful of photons are there in one bit when you do 100 gig, right? And 100 gig, the 10 picosecond bit interval, you just have a handful of photons, and that's at the theoretical limit. And by 2013, it became popular. Actually, it could have been done earlier. I think it could have been probably done 10 years earlier, but there was no demand for 100 gig. It died down because there was so much surplus of bandwidth around 2000 that all the companies that laid fiber around the oceans all went bankrupt. And you might not know that one of them, Tyco Global Networks, was actually purchased by Tata's Tata Group, and that is today part of Tata Communications. Coherent. So Coherent is the foundation for high-speed, high bitrate communication. I'll just give you here a perspective that we went from 100 to 200. Today, most systems use 200 gig per wavelength, okay, not 100. 100 was sort of done and dusted a few years ago. You can also go 400, 600, and even 800 gig, but this is mostly in a metro environment, not long haul. You can also do fractional data rates, and I'll tell you how so people want to say, well, I have a requirement to do 300 gig because I have too much, too good signal to noise ratio to stop at 200 gig and not enough to do 400 gig. So you can actually do any fractional data rate at multiples of 50 gig. So that's also possible today. Modulation schemes, 16 QAM, 64 QAM. I'll assume you know what this is, but I think Professor Thiagarajan did explain briefly. You can also do hybrid, and I'll tell you, or fractional QAM. I'll tell you how that happens on the next slide. In terms of power and density, a 100 gig module when it came out was big, 5" by 7" used to consume nearly 100 watts. Today, it's a fraction of the size and consumes just 12 watts. Okay. And we could fit a number of them. So when we started 10 years ago in 2010, we could just bid 100 gig module into the front panel of our telecom system. Whereas today we can fit 32. So densities have gone up. So there's been a significant advance in making it smaller and low power. Now, so you could cheat when you're setting records by minimizing the distance. So the correct way to look at all optical communication records, and there are two sort of Olympic games that get played. One in Europe in the ECOC conference and one in America in the OFC conference. And every year new records are set. Okay, so I'll explain what this means to you because I'm challenging people who are here, especially the next generation, to go and set new world records. So that's the first thing. If you want to win medals, you have to take part in the Olympics, right? So let's follow our athletes and see if you can set new records at these conferences. SE spectral efficiency. The erbium doped fiber amplifiers can amplify 4.5 terahertz in C and L bands. So together it's about 9 terahertz, and that's those are the rules, right? You can only use this much. Okay, so in 2014, if you look at the first line, you could achieve 54 terabits. Okay, over a distance of 9,000 kilometers. So that means that's pretty much good enough to cross any ocean anywhere. And I think on the Pacific, it's just about 9,000. And so you get the spectral efficiency, distance bandwidth product as 55, whatever the units are. Okay, so this is the number to look at for the record. So that was 2014. In 2017, you could do 71 terabits over almost 7,000 kilometers. And the world record is 51 terabits over 17,000 kilometers. Here they distributed a very long distance, and that was a record in 2017. I don't know if it's been improved beyond that. This paper is 2020, so I think they probably couldn't do any better than that in 18 or 19. So this is the world record. Okay, so if you want to do better, you need to improve this. Now, when I started in optical communication, in fact, my boss at IBM, Paul Green, whom I revere very much, he wrote actually the first book on optical networking, and then Rajiv and I followed with our book later. He said, optical communication has simplified everything, and he used to pull my leg. He said, all your communication theory is not needed. I came from communications and all that. So he said, we don't need modulation schemes, 64 QAM, and you don't need all these error correcting codes. But today, all of these records will be possible only if you use the most powerful error correcting codes. It's a combination of, there's actually 2 layers of coding, Reed-Solomon codes, turbo codes. All of them are extensively used and in all long haul fiber optic links. So without it, none of this would work. So that's something I want to emphasize. Okay. Professor Tyagarajan also touched upon multiple bands. Okay, in summary, I want to tell you that to use these bands, you need amplifiers. And you need amplifiers of different materials. For C and L band, you can use erbium amplifiers. For other ones, you need praseodymium, bismuth, thulium. None of this is practical. So multi-band optical transmission is today not practical. Okay, so the only thing that's practical in terms of multi-band transmission is C and L band. But there are many problems in using C and L band. First of all, it's not cost effective because you need separate amplifiers for C and L bands. And L band amplifiers are more expensive, okay, and have worse noise performance. And L band interferes with C band. So the summary I want to leave you with is C and L band started because you could not change the fiber that was laid, okay, especially undersea fiber. And there was a need to eke out more capacity out of that fiber. Today, if you're laying new fiber, if you have another core, you can skip L band because sending one more C band signal over a second core is more cost effective and much better. So this L band infatuation, if you will, is a historical accident. So you should really focus on doing better in the C band. Another thing I want to tell you is how do you do this 600 gig, 100 gig and so on. So the bandwidth doesn't really change. You have about in the C band, enough space for whatever, 35 nanometers. So that's around a few hundred. So you can do about 40 channels of 100 gigs. So I think about 4, whatever the math is, right? So 4 terahertz. That's how much the bandwidth is. Okay, so in this you have to fit various signals. So let's first take the 200 gig, right? So suppose you want to send 200 gig signals. You could do on the right, you could do QPSK. You get 2 bits per symbol, but the 200 gig signal will occupy around 70 gigahertz of bandwidth. So you could do, maybe 40. If you do 100 gigahertz spacing, you could do about 40 channels. Whereas you could also use 32 QAM modulation scheme, in which case you will fit this into less than 30 gigahertz. By the way, nowadays channel spacing comes in multiples of 6.25 gigahertz. So it used to be 100 gigahertz, then 50 gigahertz, and then instead of doing 25 and so on, they said you can use any multiple of 6.25. So maybe you would use here 32.5 gigahertz per channel, and so you can fit more of them, right? But this is 32 QAM, so you have 32 different signals here, so you give you 5 bits per symbol. But with this, you can only go. You require an SNR at the end, at the end of about somewhere 15 to 20 dB. So you can only go like a few hundred kilometers, to 200, 300 kilometers. If you nearly know a long distance, few thousand kilometers, you are stuck with QPSK and maybe only 40 channels of 200 gig, right? Maybe you could do a little bit more, 60, 80, but not more than that. 100, now you may have, and in practice this is true, you have an SNR of 10 dB. That's not good enough for you to do 16 QAM, but it's more than good enough for you to do 8 QAM. So people are greedy. They said, like, can I get something in between? You can. You can do alternate 8 QAM and 16 QAM, and yeah, maybe the 16 QAM will have slightly more errors, but your error correcting codes will take care of that, and so you can actually achieve almost anything on this line. Okay, so you can achieve almost a continuum of modulation schemes. 100 gig is similar, for really long distance communications, we're talking like 10,000 kilometers transoceanic, you still do 100 gig and you do 1 bit per symbol, and you could do 2 bits per symbol, but then you are down to only a few thousand kilometers. The same technique is used for 200 or 300 gig, 400 gig, 500 and 600 gig. 600 gig, despite being touted as the highest bit rate, can only go tens of kilometers. It's only useful for metro distance communication. So this is what I want to leave you with. Apparently, you can fill in the thing with multiples of 50 gig. OTN, which is a standard in ITU, supports multiples of 50 gig transmission. Okay. Itself, I think Professor Tyagarajan made the point that there are advances in fiber, but I want to tell you that all fiber is still based on silica, which is the normal glass, right? This should say non-silicon oxide, because silica itself is oxide. Silica is the main fiber material, and we have to live with this loss, which is 0.2 dB per kilometer, which is the best we can get at 1550, or 0.35 at 1310. While this is the ideal loss, fiber loss is increased over use because of splicing. There are cuts and splices, so each splice adds half a dB of loss. I think the main challenge I want to pose to material scientists in this era of glass is come up with new glass, which is better for optical fiber than silica, which is much lower loss. And that's probably the cheapest way of getting ultra long haul communications. People have tried, and you can actually get lower loss than this in the laboratory, but I think those fibers haven't proved to be practical. So this, I think Professor Tyagarajan had the same slide, where people widely believe that because of nonlinear effects that you can't go beyond about 100 terabits. There's a physical limit, but I think this is not proven. So if you are a communications engineer, you worry about Shannon's theory, information theorist, I think proving somehow that 100 terabits is the best you can do is a good challenge, because I haven't seen any proofs. I've just seen only claims that this is the nonlinear Shannon limit. So, but practically we haven't been able to go beyond this. By the way, even for the Shannon limit in communications in the late 80s, before turbo codes, people believed that the Shannon limit could not be achieved, that there was it would require infinite computational power to do this. I was in 88, I had seminars where people said Shannon's limit is not practical, it is not achievable, then turbo cores change the whole game. So don't take this for granted. Okay, so you prove it or beat it. Now, space division multiplexing, Professor Tyagarajan has introduced the concept, so I'll just build on that and give you some practical figures that have been achieved. I think he already explained that, you know, in standard single fiber, you have one core. You could have many cores which are widely spaced apart so that broadly don't interfere. You could deliberately couple them, okay, where they interfere, and then you do a lot of signal processing to decouple. I think of all these, the few mode fiber is the most promising technology where you allow few modes, more than one, and he explained how. And you could put a few of these, into a core. But one thing I think we should do is we should keep the 125 micron fixed. Otherwise, you are cheating. So with this, where do we stand in terms of record setting? Okay. So the goal here is, long ago, you know, it used to be do a mile in 4 minutes. You know, this used to be this Olympics thing. You know, Roger Bannister did that. Now I think they do a mile in maybe a little over 3 minutes. I haven't kept up. So similarly, in optics, in optical transmission, the goal is to reach 1 petabit. Now people claim they've reached 1 petabit, but that's for 13 kilometers, 23 kilometers. You've seen in Professor Tyagarajan's slide. Here I start at 100. Even 100 is not good enough. So unless you get to a couple of thousand kilometers, which is across the length and breadth of India, I think, you know, that you've not really achieved it. So where do we stand? So these are weakly coupled multi-core fibers. This is coupled core, that means you actually deliberately couple them, right? So weakly coupled is what Professor Jagan talked about, is like multi-core fibers, and then you know, there's almost no coupling between them. Then you can have a few mode fiber, like a single core which supports a few modes. That's the diamond. And I'll neglect anything over 125 microns because, you know, as I said, that's breaking the rules. So the best you can do if you leave out the open square and circle is this purple diamond here. Okay, the purple diamond is with coupled core. Sorry, not this. This is the blue square, filled square. So weakly coupled multi-core fiber. It gives you about 2,000 to 3,000 kilometers and gives you about 300 terabits per second. So no petabit yet. Okay, the other technologies are more complex, right? For example, coupled, if you couple all the modes, you know, it's a lot more signal processing, but you actually don't do as well. And then these other diamonds, you know, few modes fiber does not do as well. So, but I think all the these technologies which do up to 125 microns have promise. Maybe the next world record, something else will get better. But I think the challenge is to go a few thousand kilometers and stick to the 125 micron limit and set records. So if you have a national vision, we should say we will reach 1 petabit for 2,500 kilometers with the 125 micron cladding limit. Okay, so that's the challenge. Sometimes you have a goal, so that might help. This is world records. In practice, NEC announced that instead of putting one core in this 125 microns, they will put 4 cores, widely separated, no coupling, and this is what they plan to lay as the next undersea fiber. Okay, so that's practice is you get 4 times. I will now conclude by telling you that there's been very limited progress in the 21st century. 20th century was the, you know, heyday of optical communications. Coherent came in the early 21st century, but if I say last 10 years, 12, 15 years after Coherent, if I take 2008, all very little progress. First, even over 50 years, I think we have not progressed in making new fiber beyond silica. So the year of glass is a good year to start. Okay, because we want to reduce this loss barrier from 0.2 dB per kilometer to much less. Capacity improvements. In this century, we've got to maybe 100 terabits over 1,000 kilometers for a single core. For going to 300 terabits, that's the record I showed you, we need multiple cores. And reaching 1 petabit per second requires a larger diameter fiber today, right? And I think so we should try to reach 1 petabit without larger diameter fiber. So in the first 2 decades, you know, I start with 1990, I think we had orders of magnitude gain, 10x at least or more. In the last decade, we have only 4x gain, and that too is reached by multiple cores. So we really are struggling to improve. Optical amplifiers, EDFAs are really late 80s technology, Raman is 90s, nothing. 21st century, no progress in optical amplification. So I want to conclude by saying we need new breakthrough ideas to keep up with the bandwidth requirements of 6G. The 5G is passé. 5G is already there. You already have 5G phones. You're waiting for 5G. And today's optical networks will take care of 5G. But 6G, this conference will be held with holographic communication. So it will all be holograms. So you can see in 3D. I don't know why anyone would want to see me in 3D, but if you want to see me in 3D, you can do that in 6G. But then you need a much more optical bandwidth to keep up with the needs of 6G. Okay. While I delivered this talk, I want to thank Dr. Partha Palai, who's a student of Professor Tyagarajan, and Jishnu, who actually prepared much of the content of this talk. So I'm only the delivery vehicle. So I thank them. So we'll stop here. Thank you.
Thank you, Sri Kumar and Raj. So I would like to invite our next speaker, Sri Atul Kumar Gupta, sir. He is from CDOT. He will be delivering his talk on passive optical network, evolution, challenges, and future. Atul Kumar Gupta, sir. And let me just give a brief introduction of him also. Sri Atul Kumar Gupta, sir, has more than 29 years of experience in the design and development of optical communication based product. He has worked on design of synchronous digital hierarchy based systems, fiber access system, optical amplifier, gigabit capable GPON, dense wavelength division multiplexing equipment, quantum key distribution, etc. He holds BE degree from Electronics and Communication from Delhi College of Engineering and MTech in Optoelectronics and Optical Communication from IIT Delhi, and he is currently designated as Head Optical Technologies at CDOT. Over to you, Atul sir. Please proceed.
Am I audible?
Yes, sir. Yes, sir. Please proceed.
The screen is visible?
Yes, sir. Yes. Please proceed.
Good morning, everyone, and thank you for this opportunity. So the talk is titled PON Evolution, Challenges and Future. So I will be talking about the passive optical network. This is the agenda in brief that I wish to cover. So first, there will be a brief introduction about the passive optical networks. What are passive optical networks exactly? What are different architectures, topologies? Then I will move over to gigabit passive optical network, which is the dominant type of passive optical network that we see getting deployed today. Then the deployment of GPON in the BharatNet project, India's BharatNet project. Then what is beyond GPON, like XGPON, XGS-PON, NG-PON, to the higher capable, advancement in PON. Then what are the challenges in the PON deployment, and what are the upcoming PON standards from IEEE and ITUT. And there will be some slides on the CDOT portfolio. So this is going to be the main agenda of the talk. Just a very basic introduction. So we have, as far as broadband communication, last mile is concerned, traditionally it is based on copper or wireless, but then the thought came maybe around 35 years back, why not use fiber in delivering broadband, robust broadband at a, larger distances, lower cost, etc. So PON evolved from that very basic thought that fiber is not only suitable for core and aggregation networks, but it can as well be deployed in the access network.
Atul sir, sorry to interrupt, sir. Please, your PPT, just do it in slide slow mode. It is right now.
Okay.
Please.
Yeah, sure. Sorry for that. Is it okay now?
No, okay? Sir. No, sir. Just full slide slow mode. This
is full show only.
Sir, you have selected that screen share or not? Full
yeah,
screen.
I have done that. It's already screen share.
Okay, we are able to see your, but it is not in slide so slow mode, sir.
It's okay. Let us proceed.
Yes, sir, please proceed, sir. Yes.
So why the name came as passive optical network is that it only used unpowered splitters between the central office and the end user. So there are architectures where the end user is not directly served by fiber. but in a typical FTTH scenario, there is no active element between the central office and the end customer. Since it is basically having splitters and combiners in between, it is a point to multi-point topology. There are no active elements in between, and the downstream signal is broadcast to everyone. And the upstream, there is certain mechanisms which are put in place so that multiple users can actually use a single fiber infrastructure simultaneously. Again, British Telecom first proposed passive optical networks way back in 1987, and IEEE and ITU-T are leading the standards for various PON topologies. So in a basic passive optical network, we have mainly three elements. One is the optical line terminal, which is the central office equipment, which connects the passive optical network with the network connectivity. We have a distribution network essentially consisting of fibers and the splitters, combiners, passive elements. We have an optical network terminal which resides in the customer premises, and it provides customer with various interfaces. And then we need something to manage the whole system from the central office. So that is the LCT or element management system. So these are the essential components, but as far as technology is concerned, it's essentially OLT, ONT, and ODN. This can show in a pictorial form that we have an optical line terminal, optical network terminal. In between, there is an optical distribution network, and these are all the powered elements. There is a network connectivity provided. This is central office equipment, which controls the entire network through local craft terminal or element management system. And traditionally, PON used to earlier support asymmetrical bandwidth, meaning thereby that the downstream data rate is different from the upstream data rate. Downstream means from OLT to ONT, and upstream is the reverse direction. And the way the PON ODN is laid out, it is very easy to support distributive services, which are one way, like video broadcast from OLT to all the ONTs. There is no reverse path. So PON.
Sir, just sorry to interrupt. Sir, are you changing your slide? Because we are on third slide only, that introduction to PON.
Yeah, I am changing it. Is it not changing there?
No, it is. We are on third slide only, sir. Please, I think
you have to unshare and then share again. So
right,
then it will become fine. Yeah. Please do it again. Perhaps it will become.
Is it visible now, sir?
Yes, sir. Now it is on fourth slide. Yes. Yes, now it is moving, sir.
This is the slide with the diagram. Is it there?
Right now it's first slide.
No, but I am changing it here.
Again, it is locked on that.
Video band kar diye, bolo video band.
Sir, please, I think switch off your video. Maybe bandwidth problems. Now, please change, sir. Right now we are on first slide. That PON evolution, challenges, and future.
Is it changing now?
No, sir. Yes. Now.
Is it changing?
Yes, sir. Now change again, sir. Just from 2 to 3rd. Just go on 3rd slide.
No.
Yes, sir. Now. Yes, sir. Please proceed.
Should I go to screen that full screen mode or continue like this? I think full screen has
full screen mode is okay, sir. Please, if you.
Full screen?
Yes, sir. Yes, sir.
Is it changing now?
No, it is not.
It is not full screen. So it is again this normal mode.
I think we'll go back to the original mode. I think otherwise. Is it changing now?
No, sir.
No, it's not changing.
Yeah. You were on fifth slide now.
Yes.
If you have a PDF file, it will work much better.
Is it changing now, sir?
No, it is not. Screen is not there, sir.
Actually, sharing is stopped. आपके पास इनका स्लाइड है क्या सुभाष?
हाँ सर एक बार
आप शेयर कर लीजिए.
Sir, is it changing now?
Yes,
yes.
you are on 6th slide now. So,
Can
yeah, it is
I
changing.
continue with this? I think full screen has
Yeah,
some
yeah.
issue.
Yeah,
Okay,
yeah,
sir.
please do that.
Only thing, animation will not work, but let me continue with this only then.
Yeah,
Okay,
yeah.
sir.
You are on 4th slide now.
Now the slide with diagram is there, 5th slide.
Please change.
Yes, sir.
It's okay. Good.
Okay,
It's
sir.
5th now.
Thank you. Sorry for the trouble. Now, so what I was mentioning is that the PON architecture is inherently suited for distributive services, one-way distributed services from the central office to all the customers. That is from the OLT to the ONTs, because in between there are splitters and combiners through which the distributed services can be rolled out. So what we saw in the earlier slide was just a simple tree topology. We can actually implement PON in any topology. It's a bus, linear, distributed topology based on the customer distribution profile. We don't need to, restrict only to single stage of splitting and combining. Only there are certain constraints which we need to keep in mind while designing the PON network, that we have a fixed optical budget. We should not exceed that from ONT to OLT. So the budget will get consumed in because of the fiber loss, as well as for the loss introduced by the splitters which are there in the ODN. Then there is another limit of the maximum differential distance between different ONTs. Even if the optical budget is there, two ONTs on the same PON network cannot have a differential distance more than a certain value, because then the process of ranging, which starts in the beginning when the PON system is switched on, will not be able to control. There is a limit on the fiber length. So suppose even if there are no splitters, combiners, still the fiber length cannot go beyond a certain value. Again, because of the reason that the PON protocol requires some sort of ranging to take place when the systems are powered on at the first time. Then there is a maximum limit of number of ONTs which can be put on any PON system. So these are some topologies. We can have OLT and ONTs in a distributed manner connected in a bus form of topology, or we can have a distributed topology. We have cluster of ONTs, and then they are connected through multiple splitters and combiners. So it need not be a simple tree topology. It can be different topologies, and there are no issues as far as PON is concerned. So what are the advantages? Why did we actually went for PON as far as access network is concerned? Because it is the only mechanism for efficient utilization of fiber infrastructure. Otherwise, a single user will not be able to consume the bandwidth that their fiber provides, and it will be very difficult to manage so many fiber terminations in the central office if every user is provided with a separate fiber connectivity. So some sort of a point to multi-point architecture is required, and PON provides that. Then it also gives very efficient bandwidth usage. Dynamic bandwidth allocation can take place between different ONTs. So one ONT may require higher bandwidth at certain point, the other ONTs may not, and that scenario will keep on changing, and those can be addressed very efficiently with PON. It will support distributive services. I already mentioned that, and it is very easy to add or remove a new ONT without bothering other ONTs. Even if one ONT fails, it won't affect the performance of other ONT. So, and implementation of asymmetrical, because earlier the thought was that asymmetrical is the way to go because we need more downstream bandwidth than uplink one. But slowly that concept is changing. But still, as PON evolved, at that time the asymmetrical bandwidth was thought to be the optimum one. There are ways to address reliability issues as far as fiber cut is concerned or hardware failure is concerned. So there are robust mechanisms of protection which are provided in the PON standards, and it has a very low maintenance cost because there are no active elements in between. So now coming to a specific PON, which is known as Gigabit Capable Passive Optical Network. It is based on ITU-T standards. It supports both ATM and Gigabit encapsulation mode encapsulation. Supports both TDM and data, and ITU has actually defined multiple options as far as the bit rates are concerned, downstream as well as upstream. But the most popular one is 1.25 gig and 2.5 gig downstream. So this is the one which is most prevalent and deployed in the network. So these are some of the ITU-T recommendations as far as GPON standards are concerned. So they define the ITU defines the physical media dependent layer, transmission convergence layer, how the ONTs will get managed, how they will be controlled. So ONT management and control. There are certain enhancement band recommendations also, because as PON has evolved, so that the requirement is that the PON should be able to support the higher versions of PON on the same fiber infrastructure simultaneously with the GPON. So obviously some bands are utilized for that. In case there is a requirement to go for a higher distance, then there are reach extension standards available and long reach, which supports a differential distance of 40 kilometers. Now in GPON, we use a single fiber for both upstream and downstream. So at two different wavelengths, downstream is usually 1490, upstream is 1310 nanometer. Physical reach, which I mentioned earlier, is 20 kilometers. This is the typical value. Logical reach means that even if the optical budget is available, one cannot go beyond this is 60 kilometers. The maximum split ratios, number of ONTs on one PON is restricted to 128. The maximum mean signal transfer delay between the ONT and OLT is 1.5 millisecond. And it uses TDM in the downstream and TDMA in the upstream. This is what I mentioned earlier, that in a typical FTTH scenario, the ONT will be placed in the customer premises equipment and the fiber will go all the way up to the customer premises equipment. In another scenarios, it is possible to have the fiber getting terminated somewhere in between. And from there, the customers are served with a copper. So that copper can be ADSL, VDSL, VDSL2, etc. So there are different copper technologies. So now earlier we spoke about how resiliency will come in case the fiber gets cut. So ITU has defined multiple protection options. I will just cover very briefly. You can see that there is an OLT which is connected with the splitter. Now there is a single fiber from OLT to the splitter. In case that gets cut, all the ONTs or ONUs, they will get basically loss of signal. So to take care of that, a spare fiber which is diversely routed is usually put between the splitter and the OLT, and the splitter will essentially, instead of 1 cross N splitter, it will become a 2 cross N splitter. And there will be some mechanism on the OLT side to switch from the one fiber to the other fiber in case that fiber cuts. So the advantage is that there is no change in the subsequent deployment from the splitter to the ONTs. And in case the main fiber, the feeder fiber gets cut, there is a protection available. So this is a very simple to implement and takes care of scenarios where services of all the customers are getting down because of single cut. There are other mechanisms through which we can actually provide hardware redundancy. So in the first mechanism, it was only the fiber cut. Now, if the hardware at the OLT side is also made redundant, so even hardware failure at OLT can be addressed besides the fiber cut. And in case there is a requirement to actually take redundancy all the way to the customers, then the fiber, diversely routed fiber, can be laid up to different customers, different ONTs or ONUs. And then even if there is a cut in any part of the network, the services can be restored on a different fiber. Then there are mechanisms which provide against failure of splitters also. So these are certain mechanisms, but obviously there is a trade-off between the cost and performance in this case. So another popular standard that we know is the EPON or the Ethernet PON, which evolved from the IEEE standards. So just a brief comparison between the GPON and EPON. So GPON is, as I mentioned earlier, 2.5 gig downstream, and the most commonly used is 1.25 gig upstream based on ITU standards. EPON is symmetric 1 gig. IEEE standards, typically they are not defined in that detail which ITU defines its standard. So most of the implementations of EPON usually support 32 ONUs. And there are different mechanisms in which quality of service, etc., can be supported via GPON as well as EPON. In general, GPON is much more specified in ITU has specified GPON is much more detailed compared to the IEEE EPON standards. So coming to the BharatNet and GPON, we know that National Optical Fiber or BharatNet, it aims to connect all the Gram Panchayats with OFC, with the district. And it is world's largest rural broadband project. Rightly, it uses GPON for connecting different, for connecting the district with the Gram Panchayats, because that is the most cost efficient and power efficient mechanism to do that. Bharat Broadband Nigam Limited is set up for this purpose, and it is funded by Universal Service Obligation Fund. The basic aim is to bridge the digital divide and provide robust broadband infrastructure in rural areas, because if that the connectivity from district to the panchayats are provided, then it is very easy to roll out services beyond the panchayat into the individual villages. Now, this is drawn from the BBNL. The number of Gram Panchayats where the equipment has been installed is more than 1,75,000. And this is the model where the block is connected with the Gram Panchayats. This is the BBNL's domain. Now, animation, since in this mode animation will work, but I will try to explain that how GPON is evolving. So GPON was 2.5 gig downstream, 1.25 gig upstream. So after that came XGPON 1. This is 10 gig downstream and 2.5 gig upstream. So again, the ITU defined standards for this. I will cover that. Subsequent to that, XGS-PON came. Now, in terms of standardization, it was actually XGPON 1 was followed by NGPON 2 as far as ITU is concerned. But since NGPON 2 uses multiple wavelengths in the access network on the ODN, it was found to be more costly from the perspective of deployment. So then ITU came up with XGS-PON 1. So ideally, XGS-PON should, as far as standardization is concerned, XGS-PON was standardized after NGPON 2. But actual deployment perspective, XGS-PON got deployed on a wider scale much before NGPON 2. XGS-PON is 10 gig upstream, 10 gig downstream. That's why the name S in the name, XGS-PON. And NGPON 2 is multiple wavelengths, each supporting 10 gig in upstream and downstream. So I will cover that in subsequent slides. So these are the standards, ITU standards as far as GPON and next generation PON, whether it is XG-PON, it's G.987, XGS-PON G.9807, NG-PON 2 G.989. And as you can see, NG-PON 2 supports multiple wavelengths, 4 each in downstream and upstream. So the aggregate rate becomes around 40 gig. Besides the rate, they have allowed more splits. Instead of 1:128 for GPON, it can go to 1:256. Of course, this will depend on availability of optics, which can support such type of split, because these splits mean more loss in the ODN. The optics at the NG-PON 2 ONT is tunable, whereas optics at OLT operate at fixed wavelength. So this was one of the reasons that since the optics is tunable, the cost of the ONT was pretty high, and because of that, the uptake of NG-PON 2 was not to the extent it was expected. And this is what led ITU to actually come up with XGS-PON standard after NG-PON 2. However, all these are defined in such a manner, the wavelengths are defined in such a manner so that they can coexist. So for example, GPON, XGS-PON and NG-PON 2, they can all coexist together on the same fiber infrastructure. XG-PON 1 is not really there because it doesn't give symmetric bandwidth, which is the requirement nowadays. These are the different wavelength bands. Traditionally, GPON upstream and downstream have seen in 1310, 1490. So NG-PON 2 upstream comes here around 1530 to 40. Some space is there for the RF one-way distributed services to be rolled out. Then there are different wavelengths provided for NG-PON 2 downstream and XG-PON upstream. Now, this will actually, it would have worked better in animation, but I will try to explain it. So in a traditional OLT deployment, we have an OLT chassis in the central office, which has all the line cards which are providing GPON interfaces, and those goes towards the ODN, and from there they go to different ONTs. Now, what XGS-PON deployment, how it can take place is that some cards of the OLT chassis can be replaced with the cards of the OLT chassis can be replaced with the cards of the XGS-PON, and a new coexistence element can be introduced. The purpose of introducing coexistence element at the central office, it's a passive element, is to actually combine multiple wavelengths corresponding to GPON and XGS-PON onto the same fiber infrastructure. Now, after that splitter, certain ONTs which are there, they can be upgraded to the XGS-PON ONT. So it can be a mix of GPON and XGS-PON, or it can be all XGS-PON in the entire ODN, and GPON can be phased out. So there is no need to roll out a different, lay a different fiber infrastructure or put in totally new hardware at the OLT side. The existing hardware can be made use by plugging in the appropriate line cards corresponding to XGS-PON and only changing some of the ONTs to new type of ONT which can support XGS-PON. Subsequently, it can be further upgraded to NG-PON2. Some of the line cards, they can be made which supports NG-PON2, and since NG-PON2 has multiple wavelengths, a new passive element needs to be put in the central office which can multiplex and demultiplex, multiplex in the downstream direction and demultiplex in the upstream direction. Again, it can run on the same fiber infrastructure. So we have three different types of ONTs now: standard GPON ONT, then XGS-PON ONT, 10 gig downstream, 10 gig upstream being shared by all XGS-PON ONTs, and the third type of ONTs which are supporting NG-PON2. The intent of ITUT has always been to make use of the existing fiber infrastructure and provide wavelengths, wavelength bands which can coexist on the same fiber, so that the operator is not required to roll out a new fiber plant for this purpose. Now, some of the challenges which are there in the PON deployment. Faulty splitter is one issue. Then, since at the splitter side, we have multiple fiber terminations which are going to the end customer. So it is possible that some of them may get, swapped up or wrongly plugged. So those are issues, because in a traditional optical communication, it is point to point. So that issue is not there. Dirty connectors, bad splices, then interoperability between OLT and ONT vendors, right of the way issues frequent. Another issue which is important is the remote fault localization. Accurately localizing a fault in the fiber post splitter is really a challenge. It is easy to identify the section, but where exactly the fiber cut has taken place, particularly in the scenario where there are multiple stages of splitting near the customer premises, it is really a challenge. Then there are certain aspects of rogue ONT which keeps on transmitting continuously, which creates problem for the other ONTs, as well as the alien ONT or some other type of a device coming on the PON network, which is jeopardized, which is basically affecting the services of all the other legitimate ONTs. Those are the issues. Now, in terms of points of vulnerability, we have from the central office side, there can be issues of although the probability is less, but in case there are bad splices or bands or dirty connectors, it's going to customers because it's the main fiber. After splitter, there can be fiber breaks, but that will get limited to not all customers, but to a certain section of customers. And in the end, if we have issues where the probability is very high, because that is really not managed, unless it is managed well, we have issues of alien or rogue ONTs or damaged or dirty connectors. So these are the certain challenges which are specific to PON deployment. Now, these are some aspects of how PON is going to grow. Only thing that I would like to highlight is that by 2025, the rural India is likely to have more internet users than its urban counterpart. I think that's a significant, because till now the consumption in rural India is not as high as in the urban counterpart, although the population is the other way around. Now, this will just to show the PON standardization roadmap. Certain things are covered earlier, but what I would like to draw your attention is that ITU is already working on and has actually released a couple of recommendations related to 50 GPON. So it's a single wavelength, 50 gig downstream, 50 gig upstream, 49.76 to be accurate, and single wavelength. So this is what ITU is coming up after the XGS-PON, which got standardized after NG-PON2, as I mentioned earlier. Now, subsequent to 50 GPON, there is work going on, what is known as super PON, and which can actually support multiple wavelengths, more than 4 up to 16, and 10 gig per wavelength, 10 gig downstream, 10 gig upstream. And interestingly, this is done by both ITU and IEEE in a collaborative manner. Earlier, the IEEE was following this trajectory that EPON, they started with 1 gig, then 10 gig EPON, then 25 gig / 50 gig, where we have 1 or 2 wavelengths. One wavelength will give 25 gig, 2 wavelengths will give 50 gig. Finally, they seem to be converging onto what is known as super PON. So this is just a tabular form of the same. We have super PON from ITUT and IEEE. These are the recommendations they are working on, and can support up to 16 wavelengths in both direction at 10 gig rate. So we have at CDOT, we have variety of OLTs and ONTs. I'll just rush through that. You can see that we have chassis-based solution as well as pizza box for multiple ports, 16 port, 8 port, 4 port, etc. For the OLTs, they support then XGS PON OLT and NG PON 2 OLT is also there, both in the chassis form as well as in the pizza box. Variety of ONTs to supporting different interfaces in terms of Ethernet or ports or the standard or the Wi-Fi, etc. USB. There is a EMS and LCT. I'm not going to detail of that. Just to conclude, ITU and IEEE, they are leading the PON standardization efforts. So GPON deployments, it dominates the Indian market. EPON is also popular. Actually, EPON got standardized and the solution was available much before GPON. So EPON got deployed in a lot of countries, South Korea, Japan, etc., China. And demand for fixed wavelength PON is more compared to tunable because of cost reasons. PON technologies continue to evolve, higher speed, higher reach, more split ratio. Due to the coexistence of legacy and new PON, multiple wavelengths are multiplexed onto single fiber, making the fiber security and fault diagnosis crucial. So the issue of fiber cuts, etc., it is going to affect much more than ever. CDOT is working on PON technology, and it has actually taken a leading role in BharatNet to bridge the digital divide. This is all from my side. Thank you very much.
Thank you, Atul Gupta, sir. Thank you very much. And I want to tell all the audience that there is a dedicated question answer session also in the last. So if you have any question, you may ask all your questions in the last. So now I would invite our next speaker, Sri Anjani Kumar Vaisji. He will be delivering talk on trends in optical networks and technology. And, Sri Anjani Kumar Vaisji is his Director of Field Systems Engineering at Siena International Region, where he is responsible for all the pre-sales, business development and solution engineering activities in Tier 1 accounts for India and SAARC region for more than 10 years. Given his experience in optical networks, he also works with global teams across the Siena International Region covering Europe, Middle East and Asia Pacific for knowledge and best practice sharing. Prior to joining Siena in 2011, Anjani Kumarji held various key engineering positions at Tejas Networks, COLT and Bharti Airtel in optical and network management domain. Sri Anjani ji holds a degree in electronics and communication from Dr. APJ Abdul Kalam Technical University. So over to Anjani sir, please proceed, sir. Anjani sir, please proceed.
Yeah, thank you, and hope I'm audible.
Yes, sir, you are audible, sir. Please.
Okay, let me share my screen. Are you able to see my screen?
Yes, sir. Sir, please make it full screen. Is that
Yeah, I'm doing it.
Yes, sir. Now it is visible, sir. Very well. Please proceed.
Okay. Thanks for introduction, and thanks for inviting me onto this webinar. So I think Dr. Tyagarajan and Dr. Kumar already talked about what is happening in terms of the fiber optical communication, DWDM, and the Coherent modem technology. And what I'm going to talk about is uh, what are the key drivers which are happening into the optical communication industry, and what is their impact when we talk about on the overall networks, when we are building the networks, how the efficiencies are bringing in because of all the optical communication trends which we are seeing right now happening across the industry. So before going into the detail of what is happening across the industry, let's see, or let's go a deep dive and understand what is happening into the market. And uh, when I'm saying what is happening in the market, it means is there are certain key application and the consumer trends which are happening at the same time. So if we talk about let's say in terms of from the application area, we know that, right? Today, it's all about distributed computing and the virtualized apps which we see or which we are using as on today. But if you go a bit in the history, around 1960 and 1970, so computing was started with the mainframes in a centralized model. And then in the late 80s until 2000, what has happened was it moved from the mainframes towards the client server distributed model. And then thanks to the mobile cloud which came into our life in about 2005 to present and brought us back to the centralized model, uh, and cloud added the virtualized application for faster service creation, which has been the fantastic as we speak. Now again we are transitioning from mobile cloud to the again edge intelligence era, where it will be all about distributing computing, and it would be keeping the application virtualized, and that is what driving the key changes into the industry. And when we talk about in terms of the key user trends or end dynamic users, right? So what is happening is we have seen from last 2.5 years, because of the pandemic, our residence has become the small office. And all the, if you say the enterprises or large companies, everyone has moved from towards the cloud using the digital transformation. And of course, last but not the least, the 5G is going to be in our life very soon, as we speak, specifically from the India context. So all of these market dynamics are actually driving the changes of the current and the future communication trends, and that's what I'm going to cover in the subsequent slides. So there are four major key technology trends in optical communication that I'm going to cover today. One is the coherent modems. So when we are talking about the coherent modem, so it is reach, performance, and high capacity. That is what we had seen in the previous sessions as well. And on top of that, the footprint and the performance optimized. So there are two, I would say, as far as coherent optical modems are concerned, there are two ways wherein the industry is developing as on today. Then the next one is the networking platforms. So now all these coherent modems have to be used in some way or other way in the networking platforms, because ultimately we have to build the networks wherein we need to pump in the capacity, and serve and the operators or service providers or all the OTTs need to drive the capacity and connecting the two P's into the network. So there is a lot more requirement from the flexibility and the openness which are being built into the networking platforms, and that's what I'm going to talk about. And then advanced network architecture. So based on the whatever happening into the core and modems and the networking platforms, what are the new network architectures that we will be seeing going forward? So I will touch upon onto that one as well. And the final and the last one, I would be talking about some of the software control and analytics, and through the advanced applications, how we can bring in the much more efficiency into the optical networks. Let me start with the coherent modems. So there are certain key technology areas which are actually driving the uh, development of the coherent modems. And we have seen Dr. Kumar and Dr. Tyagarajan also touched upon a couple of key things out of whatever I have mentioned here in this particular chart. So I would start with the baud. So I think we have seen we have the journey from 100 to 400, now 800, and we have seen the baud rates increment going, and that is actually facilitating the higher reaches at the higher line rates. And on top of that, there is another industry trends which is happening, the selectable baud. With the help of selectable baud, what we can do is when we are building the networks, we can select a appropriate baud rather than to be a fix on a particular baud, and bring in much more efficiency in terms of either line rate or maybe the number of channels or spectral efficiency into the networks. The another one is the link monitoring and enhancement. What we can do as on today with the help of advanced software developments, what is happening is we can monitor the links, and on the fly into the networks itself, we can bring in the efficiencies in terms of optimizing or ability to optimize the network designs, or maybe the pumping the more capacity on the fly when actually network is built and it is running. So those are the key advancements which are coming as far as link monitoring enhancements are concerned. The enhanced coding, so I think uh, because of the higher baud, what happens is we are able to transmit more bits onto the fiber, and the enhanced coding gain actually helping us in order to drive much more capacity and the spectral efficiency, especially at the longer distances when we talk about, let's say, long haul or the subsea applications. Probabilistic constellation shaping, I think this is the important fundamental, because when we have to use the higher baud and higher modulations, what we have to do is we have to send much more symbols into the fiber. And what happens is, because of the higher modulation, the distance between the symbols are getting closer and closer, and that is actually the important factor, because when Euclidean distance between the two symbols are getting closer, it could lead to the nonlinear performances. And wherein the probabilistic constellation shaping comes into the picture, wherein what we do is we distribute uh, the constellation depending upon the energies, right? There would be a lower energy and there would be a higher energy. And since the higher energy would have much more impact as far as non-linearity, so what we can do is, using the probabilistic constellation shaping, we can prioritize, let's say, lower energy signals going into the fiber. And the last one is the nonlinear compensation. Actually, this nonlinear compensation is majorly important piece when we talk about the long haul and the subsea application, and that is being driven through the probabilistic constellation shaping as well as enhanced coding gain. Now going all this, there are two major, I would say, developments are happening or has been developed, and going forward, we will be seeing the improvement in terms of the line rate. One is the performance optimized. When I say a performance optimized, it means when we need to drive the larger distances, and then the footprint optimized is actually when we need to fit in the coherent modems into the specialized platforms, wherein we need to bring in the space as well as power efficiencies. So what is happening? So we have seen, we talked about 100 gig, 400 gig, and then 800 gig, and 400 gig ZR is there already. We have. What is next? The next is probably we will be enhancing the line rates and going to have the 1.6 terabit uh, line on a single wavelength over to the fiber. And from the pluggable optics standpoint, we will also going from current 400 gig up to 800 gig, again with the lowest power, smallest footprint, and the driving the maximum spectral efficiency with the performance optimized mode, or the coherent card, and driving the longer reaches. Now the next one I'm going to cover is the networking platforms. So if we see the especially onto the routers world, right? When we were having only onto the 10 gig switch, so optics components were and the switch commons component were actually driving the cost as a 50-50%. But as we move now, what is happening today is the optics component is actually going higher as compared to switch and commons. So actually that is actually driving the IP optical convergence use case, and there wherein I think everybody in the industry is working towards in order to have the optical IP convergence wherein the coherent pluggables are being used into the routing words or routing platforms, similar to the way where we have seen the TDM platforms wherein the coherent uh, plugs or coherent cards were actually integrated with the TDM platforms in the past. Similar trend, but what we are seeing is happening today into the industry, wherein IP optical convergence or integration is happening, and the coherent plugs are actually playing the major role into IP optical convergence. And we would see in into the subsequent slide how it is bringing the efficiencies into the networks. The one is, I think, Shannon limit. Dr. Kumar already talked about. We are going closer to the Shannon limits, and there is always pressure into the service providers networks that they need to have the high availability. And again, because of the lot more automation and the artificial intelligence which is happening across the industry, so there are three major components which are actually driving the, first of all, C and L photonic system. So this is a bit different from the C plus L, the traditional system, wherein we can uh, pull the entire spectrum with the either with the wavelength or maybe the channelized AC, and we can mitigate the key aspects of the C plus L, the legacy systems, wherein because of the SRS impact, there is a power transfer which was happening from C to L band, and because of that, the performance of the C band was impacting. So that is something which is being mitigated with the C and L band and with the help of the channelized AC. And on top of that, what is happening is uh, this is actually driving the faster restorations or convergence time when we have to work on the especially onto the layer zero control plane or the WSON environments. The another is the automated and the flexible photonics. So there are a lot more development which has been done, especially into the ROADM area, and there are tools which are available now into the industry wherein we can see what is the optimum ROADM structure or a drop structure that we can use in order to increase the capacity, specifically when we are
Anjani
driving.
ji, sorry to interrupt you. Your voice is splitting. So if you also please switch to your videos.
Is it okay now? Hello, are you able to hear me?
Yes, your voice is splitting. Please proceed, sir.
Okay,
Please switch off your video and proceed, sir.
okay, okay. Give me a second.
Yes, sir.
I hope my slides are still visible in the full
Yes, slides
screen
are
mode.
visible, sir. Yes.
Okay, good.
Only
Thanks.
your voice is splitting. That's why. Okay. Please proceed,
Okay,
sir.
okay. And I think the last one is the open platforms wherein the netcon, gRPC, and the SNMP and the open config, those kind of protocols are being now supported into the optical platforms, wherein it is allowing us to have the integration and doing the all the artificial intelligence and taking the telemetry data directly from the components and doing the analysis and bringing in the further efficiencies into the market or into the networks, which I'm going to talk about in the subsequent slides. The third one is the advanced network architectures, what is happening, and special focus or the key focus in today's network as far as advanced network architectures are concerned. Those are into the metro and the edge network architectures. And if we see what is happening into the metro and edge architectures, so we had seen previously, like in the year 2013, 2014, uh, up to 2016 or 2017, the networks were built, let's say 7 to 9 nodes in a network, and it was majority of the traffic was mobility traffic. And this I am talking about in terms of the India market environment and the India application use standpoint. And the granularity of services at that point of time was 10 gig or maybe less than 10 gig or sub 10 gig services into the especially into the metro networks. Then uh, all these hyperscalers came into the market, and the growth of the traffic has got multifold. And today we see um, in all of our homes, Netflix and Amazon Prime and all these OTT platforms are actually part of our daily life, and these are actually driving furthermore capacities into the network apart from the mobility. And when I'm talking about the mobility, so 3G to 4G and now 5G, so that is also going to give us much more capacity requirement into the metro and the edge kind of networks. And we have seen the metro networks going to have from 7 to 9, now 15 to 20 nodes going into the metro network. But as we saw in terms of the market trends, what is happening, and the edge intelligent edge, what we see going forward is again the metro, the core would be entire metro would be divided into the two parts. One would be the metro core, and the another would be the metro edge. And metro core would again be a 5 to 7 or 7 to 9 nodes, and the larger portion of the network would become part of the metro edge. And they are specific ingredients or I would say the components of the optical communication, which would become part of the metro core and the metro edge. So first of all, whatever advancement we are seeing as far as the photonics are concerned, that would drive the metro core part, and we have to select a proper infrastructure or a architecture when we need to build a metro core type of architecture. The layer zero control plane would be ingredient part of the metro core network architecture, because the number of fiber cuts and the fiber environment what we see in India, and it could be a C or C and L depending upon the fiber availability. Specifically, when we talk about the metros, the laying of the fiber is a Herculean task as we speak today. So C and L kind of platforms become much more relevant as far as metro core are concerned, and the performance based optics, because what we have to do is we have to drive the higher capacities into the metro core. And there would be a multi-layer optimization that we would be seeing going forward into the edge and into the metro core, which would be happening into these kind of networks. And when we talk about the metro edge, so what we would be seeing going forward is the point-to-point and hub-and-spoke kind of architecture, wherein the edge line system kind of platform would play the key major role while building the metro edge. And the integrated coherent plugs would become part apart from the lowest cost ROADM. And because of the integrated coherent plug and the layer zero control plane, this would become part of the multi-layer optimization, which we would be seeing going forward into the metro and architecture going in 2022 and beyond. Now, the last one I'm going to talk about is the software control and analytics. So there are certain software apps and the analytics which are developed, and there are certain apps or applications which are into the pipeline, wherein because of all the key technology development we have seen in the previous slides, we will be able to leverage all of these things, and because of these advanced optical application apps, we would be able to drive much more resiliency, much more capacities into the network. The first one is because of the live telemetry or live the performance matrix of the coherent module. What we can do is we can see what is the margin which is left into the networks, and thanks to the coherent technology development, wherein what we can do is we can, on the same card, we can support the multiple line rates onto the same card. So what we can do is on the fly we can increase the line rate, and even we can it can be told to the users using the software application apps that what is the next line rate they can go, or if they need to investigate something, or they need to keep on running onto the same line rates. So those are the things which are actually bringing in further efficiencies in terms of the capacity and lowering down the I would say cost per bit for the service providers or network operators. The another important point onto the layer zero control plane. So we used to see a fixed kind of wavelength. We used to see a fixed kind of wavelength when we see into the layer zero control plane environment. When we are running, let's say on path one, let's say we are running at 600 gig wavelengths. When we have to restore in the earlier times, what we can do is we can only restore with the 600 gig wavelengths only. On the fly, we will not be able to lower or higher line rate. And if suppose there is a network condition which is happening wherein we will not be able to restore, let's say 600 gig wavelength, the entire traffic is going down. So now, because of the advancement which is happening, we are in Sienna, we call it a liquid restoration. Because of that, what we can do is we can lower down on the fly when we need to restore wavelengths on an alternate paths, wherein we can sustain even the larger amount of the traffic, or we can even prioritize the traffic onto the wavelengths and save a larger amount of traffic when we need to restore on an alternate path. And actually that is driving much more efficiencies, because we have seen into the networks most of the times wavelengths are running, let's say, on a shorter path, wherein we are able to support much more higher line rate. And whenever we need to go onto the restoration, we can lower the line rate on the fly. So in maximum amount of time, we would be driving much more higher capacities into the network with the help of these software applications and the automatic intelligence or AI bringing into the networks. So in summary, there is a lot more which is happening from the optical communication trend standpoint, and we are leveraging in a different ways in order to bring in the much more capacities, efficiencies, driving the cost per bit, and increase the capacity for the service providers and the network operators. With that, I would thank you for giving me the opportunity for presenting to this seminar. Thank you very much.
Thank you, Anjani sir. So now we have come to to the last speaker of the today's technical session. So next speaker is Sri Nitiraj Singh Sekhawat sir, optical technology expert from Infinera. He will be delivering talk on advancement in optical technologies and future network. Sri Nitiraj Singh Sekhawat sir is Director Systems Engineering in Infinera. He has 20 plus years of experience in telecommunication, worked in various roles, including field operations, system integration, TAC, and recently in pre-sale system engineering from the last 8 years. Expertise in optical DCI, metro, long haul, and subsea network. Mr. Sekhawat is currently heading Infinera South Asia pre-sale system engineering team. Over to you, Sekhawat sir. Please proceed.
Thank you, sir. Thank you very much for the introduction. Let me just share my slides and then I'll start. So let me know if you can see my slides.
Yes, sir. Yes, sir.
Okay, I'll just put it in the slideshow mode. First of all, I'd like to thank you and being honored to be speaking on this platform. And I also want to thank Professor Thyagarajan, Kumar Shivarajan, and Anjani, who has given a great presentation. So the topics which I'm going to cover will be actually maybe already covered at some level by Professor Thyagarajan or Mr. Shivarajan, and also Anjani, who's an ex-colleague. but I'll try to cover them again, maybe to re-emphasize and maybe come to a few additional points on these particular topics. So I'll start with advances in, let me just get my pointer, just a second. I'll start with what we have seen the advances in transponder technologies from 2000, where we were going, I think, 100 gigahertz with the 10G kind of line rates, then 50 gigahertz, where we are able to run 80 channels of 50 gigahertz, then 160 channels. This was basically based on IMDD, or direct detection, intensely modulated direct detection. And somewhere around 2008, 2009, the coherent starts coming in. And we start seeing with coherent technology, wherein we are able to lock in the particular frequency at the receiver, which provides a better performance. We are seeing 40G kind of line rates, then subsequently 100 Gbps. Then there was advancement in something like extended C band came in, wherein we could do a 4.28 terahertz in C band, and we could do 50 gigahertz, 96 channels of 50 gigahertz. So that led to 9.6 terabit of capacity. Then came 16 QAM, which doubled the capacity, and then flex grid ROADMs and more flexible architectures on the spectrum usage, like mentioned by Mr. Sivarajan, like 6.25 gigahertz or 12.25 gigahertz kind of technology, which allows to pack in more number of channels. So basically, the spectrum required by the carriers reduced from 50 gigahertz to 37.5 gigahertz. And over and above that, there is something called super channel, which Infinera was doing since a long time. So this allowed us to pack more carriers within a band. And at this time, we are currently sitting on 800 Gbps technology, which was also discussed by Mr. Sivarajan. And with 800 Gbps technology, we can have a single carrier of 800 Gbps. This will be applicable for metro kind of environment, and also where Ramans are used, which do not Raman kind of amplifiers are used, where OSNR impact on the OSNR is very less. So you can see that from 2005 to 2020-21, where we were able to run 800 Gbps total in that fiber, we are able to run a single carrier of 800 Gbps. So this is the kind of technological advancement which has taken place in last 15 years. This may not happen in future, I mean, these kind of advancement, but there may be some advancement which may increase the capacity a little more, and also more focus will be on reducing the cost per bit. This chart just shows the evolution. So when we moved from first generation to second to fourth to fifth, and this is I'm talking about Infinera's generation. So there is an around 15 to 20% reduction in cost per bit. Okay. So more bandwidth, we can run it over longer distances with the evolution of technology, and lower cost per bit. Then there is spectral efficiency. So in first generation with 100 Gbps QPSK kind of environment, it was 2 bits per symbol per hertz. And at this time, we are sitting around 8 bits per symbol per hertz. So this allows to have a lot of capacity from the same fiber. And another important point I wanted to make was the number of OEMs who are doing these kind of technologies now, because it is becoming more and more complex. These are reduced from 10 to currently it's from 2 to 3 OEMs who are actually doing this kind of technological evolution. And the reason for that is the complexity has increased. So with 100G, we used to play with FEC. Then with 200G, there were 2 knobs, FECs and types of modulation, like 32 gigabaud, Nyquist subcarrier. As we move to the next generation, we came into FEC, baud rate, modulation, constellation shaping. And with current generation, there is additional, the second generation of all these, like FEC, baud rate, modulation, and constellation shaping, and dynamic bandwidth allocation. So let me move ahead. So as more configuration options are available, but there is an increase in complexity. That was the point I wanted to make. For 800G technologies, there are a few key enablers. First is the capability to do high baud rate. This is basically done in during the digital signal processing, the advancement which has happened during the last couple of years, last decade or so, which allows us to have 96 gigabaud of very high baud rate for efficient spectrum usage. Second is the Nyquist subcarrier. Then there is probabilistic constellation shaping, dynamic bandwidth allocation, then gain sharing, and photonic integration. Consider the amount of time we have. I'll just cover these two topics, and maybe we can cover those other topics later. First is this Nyquist subcarrier and PCS, probabilistic constellation shaping. So before Nyquist subcarrier, there was actually single carrier, and you can see there were these side lobes, and the signal, although it is on a central frequency, there is always a roll off which happens basically. So due to roll off around the central frequency, what happens is there is a possibility of having an intercible interference between the adjacent channels. And this is being amplified by these side lobes which are there in a single carrier without any shaping. So what was done for the single carrier, Nyquist shaping was done, so which allowed reduce the roll off, reduce the intercible interference, and allowed for a tighter spacing of the carrier. So efficient use of the spectrum. This was first Nyquist shaping. Then, and as you could see that in order to reach 100G when coherent technologies was started, we used to use 32 gigabaud or 35 gigabaud kind of symbol rate. So what we had done in that case is that we had subdivided digitally, and we call that Nyquist subcarrier. Digitally, this 32 gigabaud was divided into four subcarriers of 8 gigabaud. So this again provided additional tighter channel spacing, better sensitivity to non-linearities. How better? I'll explain that in next slide. Reduced chromatic dispersion, because chromatic dispersion is a square function of the baud rate you increase. So once we are, in this case, we are reducing the baud rate by 1/4 digitally. So there is a reduction in chromatic dispersion and enhanced lightning tolerance. This is again basically for this overhead fibers, where the which is very sensitive to lightning due to the vibrations which happen due to the lightning in the overhead cables. At this time, we are in our second generation of Nyquist subcarrier. As I mentioned, this 96 gigabaud for the current technology of 800 Gbps. So what is being done is basically these are divided into 8 subcarriers. So 8 subcarriers into 12, it makes 12 gigabauds, even tighter spacing, and enables per subcarrier modulation. Basically, what it means that there are filter penalties on the edges. Okay. And due to these filter penalties, you are not able to get the maximum or limits your line rate or which you can deliver. So with this kind of architecture, Nyquist subcarrier second generation, what we can do is we can either enhance the reach of the signal or enhance the line rate. And how it is done, that the carriers in the middle are launched with the higher line rate, and carriers on the edges are launched with lower line rate. So which allows either to increase the reach or increase the performance. That is what dynamic bandwidth allocation is, and second generation of enhanced lightning tolerance. Now coming to why we see that going to these lower baud rates or Nyquist subcarriers is an advantage. Here you can see the distortion penalty, and this is the baud rate. For these non-linearities, four-wave mixing and self-phase modulation, the best area is when the baud rates are somewhere between 2-3 gigabaud to 16 gigabaud, or 15 or 16 gigabaud. Because as you start increasing the baud rate, these non-linearities also starts impacting the system. So the first generation, I mentioned that for 32 gigabaud, 8 gigabaud subcarriers, 4 subcarriers. This generation, we are within this area where these non-linearities are very less, and 12 gigabaud, 8 carriers, 800 Gbps we can achieve at 64 QAM. So conventional carrier, if you go with 96 gigabaud, it is not going to provide you any reach and performance. And with this Nyquist subcarrier, we have better performance against non-linearities, better performance, reduced chromatic dispersion that enables dynamic bandwidth, where carriers in the middle are at a higher line rate as compared to the carriers on the edge, and overall capacity is maintained and enhanced lightning tolerance. So this was Nyquist subcarrier. Coming to probabilistic constellation shaping, I think this topic was also covered by Mr. Sivarajan and Professor Tyagarajan, but I'll just re-emphasize if we start with the conventional QAM-based coherent modulation. So there is an X polarization and Y polarization, and 2 bits, for example, if you take QPSK, so total 4 bits per symbol. As you move ahead to 8 QAM, 16 QAM becomes 8 bits per symbol in total, and as you can see, these are the constellation diagrams. So with QPSK, the distance, the Euclidean distance between the points on the constellation map are very high, very long. But as you go on increasing the modulation schemes and using more bits, you see that distance reduces, and this reduces as the distance reduces. This noise tolerance reduces significantly. And that is the reason you see that as we go with conventional modulation, there is a significant difference in the amount of distance these technologies can cover. Although you get a higher line rate with 64 QAM, maybe you get a 600 Gbps of line rate, but the distance may be reduced to few tens of kilometers or 100 kilometers maybe. So this is an important aspect which was not allowing to have higher line rates. Okay. So, and one more point I want to make in this constellation diagram, the constellation points are represented by 2 factors. So where the constellation point is basically the phase of that particular point, and the distance from the center is the amplitude. And the power of that symbol, the amount of power required for that symbol is actually square of amplitude. So what that means is, and all of these signals are basically sent with same probability. So the amplitude of, let's say, this particular symbol is X. The amplitude required is much larger because it is at the edge. So higher energy is required, higher power, and the power is basically, I think, square of the amplitude in this case. So, and everything is at same probability. So you need to send the signals in order to ensure that signals at the constellations which are being captured at the edge of this particular constellation diagram are also captured. You need to send it with higher power, whereas the ones in the middle, near the middle, are basically requiring lower energy or lower power, and probability is same. Second point, important point is, this was also being covered. So if you see, there is with conventional modulation, there is a stepped approach. Okay, if you are not able to run, for example, here 32 QAM, and if you are running, let's say, 32 QAM, and there is a distortion in fiber, there is an increase in fiber losses, you directly go down 20%. In case of 16 QAM, for example, 16 QAM 200 Gbps you are running, and due to increase in fiber losses, there is nothing in middle between 16 QAM and 8 QAM. You directly go from 200 Gbps to 100 Gbps to 150 Gbps. And similarly, from 8 QAM to QPSK, if you have to go, there is a reduction of 50 Gbps, around 50% reduction. Okay. And second is how you try to mitigate these. Either you start launching on higher power. If you launch on higher power, your maybe noise tolerance increases, but the non-linearities are also increased. If you launch at lower power, the noise tolerance decreases because you see the distance, the Euclidean distance between these constellation points also decreases significantly. So increased capacity, constellation points go closer and are more sensitive to noise. And there is a power trade-off between noise tolerance and non-linearities. And there is a limited granularity with conventional QAM modulation, like QPSK, 8 QAM, 16 QAM, 32 QAM, and 64 QAM. So just re-emphasizes what can be done is with probabilistic constellation shaping. What is being done is the constellation points which are near the center are being sent with higher probability as compared to the points which are on the edges. So what it does is basically the lower energy inner constellation points are sent more frequently, and higher energy outer constellation points are sent less frequently. This is being done due to some advancements in the technology. So what it does is that overall power or overall amplitude required, overall power required reduces, Okay, and overall power required reduces. That means that you can increase the amplitude of the signals. So lower probability, your total average power of the constellation points on the edge is reduced, and ones in the middle require lower power. So total average power is reduced. Okay, and decreases the probability of higher power outage constellation points. So with this, what happens is you are able to go in between the traditional modulation schemes. So for example, here, this is the reach. So with all 64 QAM, the reach is limited. You can go somewhere in between using this probabilistic constellation shaping. This is again gauge that can be used, and as you can see, you can go somewhere between the traditional modulation schemes, which allows you to have better end of life capacity and better line rates. And this can be achieved in an increments of 25 Gbps and 50 Gbps. So you are not limited then by this traditional modulation, and that is the reason we are able to see this higher line rates coming in with these new technologies, maximize the wavelength capacity of each according to the route conditions. That was benefit number one. Benefit number two is OSNR tolerance. So since the amplitude required is less, so since the power required is less, and power is square root of the amplitude required, so and this represents the amplitude. This particular distance represents the amplitude. So you can send the signals little away. So better you can have a greater distance as compared to our standard QAM. And between 4 and 10 bits, a symbol gain is about 1 dB. I mean 8 bits per symbol, around 0.84 dB. So this allows for the better performance of the and achieve the higher line rates. Now, if you talk about the future technologies from 200G to 600G, currently we are sitting at 800 Gbps, and there are advancements happening in the same optical engine. I mentioned that 96 gigabaud and 7 nanometer. Then there is going to be something in between where you can have 100 gigabauds in 7 nanometer. So mainly the changes in these particular generations, like for example, if you name the product i6 and i6 Turbo is, we are getting additional 4 Gbps baud rate, which provides an improvements on the higher line rates, but at the lower line rates, it will provide an improvement in price per bit. The next generation, which we are seeing, maybe would be 150 gigabaud and 1.2 terabit kind of line rates in 2023, 2024, which will further reduce the cost per bit and increase the density, and it will be based another generation of Nyquist subcarrier. Just to re-emphasize on the capacity again. So C-band, let's say, is 4.8 terahertz, extended C-band. And if we talk about this is something we did an analysis for a metro kind of network in India kind of environment. So 95 gigabaud, 100 gigahertz is required per carrier, and we can run approximately 48 carriers. And with 48 carriers at 800 Gbps, we are able to achieve 38.4 terabits of capacity in extended C-band, which means a spectral efficiency of 8 bits per second per hertz. And if you add to this the L band, I mean C plus L band, C band 4.8 terahertz, L band 4.8 terahertz. So it allows a capacity of 76.8 terabits in a single fiber pair, which is huge. And these systems are basically already deployed or are getting deployed. So you will soon start seeing these kind of capacity. And also, I think these are getting deployed in India as well. C plus L kind of approach we have is basically in order to save your cost on day one, on the same fiber, you deploy the C-band line system first. And once you reach, once the C-band line system is full, 4.8 terahertz capacity is spectrum is fully utilized, you can add this L-band line system to it. And it's a pluggable kind of approach wherein you can plug in the lines L-band EDFAs into the existing ILA site, C-band EDFAs, and L-band L-band add drop structure and existing C-band add drop structure. Okay, this slide just re-emphasizes on what I was mentioning. So you have a C-band line system already deployed. This is also applicable for Raman amplification. I am specifically mentioning here EDFA because there is some resistance for deployment of Raman in India. The reason being the high fiber losses and high point losses. But this is something which is possible with Raman amplification also. So this is your day one network. 4.8 terahertz is fully occupied. You want to upgrade with L-band. You just plug in the L-band amplifiers, and this is the add drop structure, and then add the transponders. And this is non-service impacting. So you can basically double the capacity of your fiber. So this is something also a technology which has been deployed in other parts of the world, and I think this will be soon be applicable and being deployed in India as well, which will basically allow you to use your asset to fullest efficiency. If you talk about future of optical technologies, so I think main focus or emphasis will be on the maximum performance and optimization between capacity and reach. We will see higher baud rates. Currently, we are at 9600. We will see 150 and in future even higher than that. This probabilistic constellation shaping will play a very, very important role because it is something which will allow to have the maximum out of your fiber, and Nyquist subcarrier will also play a very, very important role on all the future technologies which are going to come. Now, I think Anjani touched on this, the pluggable market. Pluggable is also, there is future. There are three kinds of developments which we are seeing. One is driven by OIF, which is like point-to-point, very short reach, low power, low cost, and small form factor for 400G ZR. Then point-to-point enhanced reach, low power, low cost. You can see this as 400G ZR plus. And there is something which we as Infinera has been working on. We call it XR. This is basically point to multi-point, enhanced reach and low power and low cost. And I like to cover this in next few slides. And this is very important. This is being globally deployed and there's multiple trials done. And this is mainly applicable for 5G and maybe 6G. And you'll see the reason. Before moving to that, the evolution on the baud rates and the processing power of the chipsets which we are seeing, like from 2010, 2012, 65 nanometer to currently we are sitting at 7 nanometer in 2020, 2021. And there is a possibility of going to 5 nanometer, and also possible that 5 nanometer may come into picture. Directly, there will be a leap from 7 nanometer technology to 3 nanometer. And I think the work is already being done by all the OEMs on this. Yeah, 32 gigabaud, then yeah. So with this, these kind of chipset, we were able to do 32 gigabaud. Then with 28 nanometer, 56 gigabaud. With 16 nanometer, we got further increased to 68 gigabaud. With 7 nanometer, we are sitting right now at 96 gigabaud. And in future, with 5 nanometer and 3 nanometer, we will be at 120, 150, or 160 gigabaud with 1.2 terabits or to 1.6 terabits of line rates per carrier. So increase in baud rate, increase in data rate per channel. And as we increase these, the number of transponders will reduce significantly. Moving on to XR. Why is XR important? So at currently what is being deployed is basically whether it is an access or coherent edge. So there is a hub location and there are trans receivers at hub location and there are trans receivers at the edge locations also. So what XR optics does is basically you have a single trans receiver. So in this case, you require N into 2 trans receivers, both at hub as well as at the edge. With XR, we have come up with a solution where you require a single transmitter at the hub and multiple trans receivers at the edge. And this is applicable for 5G as well as, for fiber to the home or small and medium enterprises. What it does is, we did a study. If there is a reduction in 50% trans receivers and eliminate the intermediate aggregation devices, increases router efficiency because All the aggregation is done at a single point and then it handed over to router, and it reduces the truck roll for upgrades. How it does that, I'll explain next slide. This is again based on our Nyquist subcarrier technology. So each single carrier, so the pluggable at the hub will be either 400 Gbps or 600 Gbps, 800 Gbps, sorry. And there will be multiple subcarriers into it. Each subcarrier with 4 gigahertz of will require 400 gigahertz spacing and will provide 25 Gbps of bandwidth. If you want 100 Gbps of bandwidth, you need 4 subcarriers, total 16 gigahertz of capacity. For 400 gigahertz, it will be 64 gigahertz. For 400 Gbps, it will be 64 gigahertz. And then in future, we'll have 800 Gbps trans receivers at the hub location, and you can have 32 into 25G of kind of line rate. And each of these subcarriers are individually routable. You will see it in next, and these will be based on MSA compliant form factors depending upon the requirement. So CFP2 will come first, then QSFP-DD, QSFP28, and OSFP. This is how it will look like. It will look like a broadcast from a 5G tower or 4G tower to multiple mobile devices. So you have a single trans receiver at the hub location with multiple carriers, as I shown, let's say 16 subcarriers, and then there is a combiner splitter, which will split these individual carriers, and these can go to a different spoke location. These can be any of the applications. And let's say on day one, you require 25 Gbps capacity. If you want to increase the capacity, then you don't need to put another pluggable at both the ends, basically. It can then be on the fly. So 50G, you add one more carrier on the fly, the total capacity available at 50 Gbps. You want more capacity, 75 Gbps, and required at particular location, you add 2 more subcarriers, and you can enable 75 Gbps capacity. So this kind of application is actually getting deployed and tested at very large scale worldwide. And we will have some engagements in India also. This will provide you high capacity bandwidth, maybe for backhaul. So it can be for DCI, point-to-point application. This is also applicable for passive ring, amplified ring, passive tree, metro aggregation, backhaul, 5G backhaul, maybe for 6G backhaul. I don't know what kind of capacities are required at this time, but it can be applicable for metro. So unamplified, it can support 20 dB. Amplified, it can support 33 dB on a single span link. And also these the amplifiers and all the components are basically hardened. Hardened means you can put them in the outside environment up to 65 degrees centigrade of temperatures. And it can have also extended reach, 400 to 1000 kilometers with 16 QAM if you have multiple amplifiers. And it's point to multi-point. So this is a very important technology, and we are looking and we are seeing quite momentum in the market for this technology. We already have done a lot of studies, and amount of total cost of ownership it has reduced in 5 years, like 70 to 75%. It eliminates intermediate aggregation, reduces truck rolls, improves efficiency. And we also have a open XR forum wherein we already have these worldwide service providers already part of it. And this forum is basically defining the compatibility requirement and establish interoperable networks, demonstrate interoperability, and more service providers are joining this basically this open XR forum. So I think that's all I wanted to cover, and thank you very much for your time. Over to you, Mr. Subhash.
Thank you, Shekhawat-ji. So with this, we come to the end of our technical session. Now we will enter into third part of the workshop. So next is question answer session. If you all audiences and are requested to please ask your questions. If you have any question, just raise your hand. We will unmute you from here, this side. Please raise your hand. Ashok Jha sir, as in you asked some question in chat. So let me see that also. If you have any question, please raise your hand. One question I saw in chat that is from Atul Gupta sir. Sir, I'm reading the question. The 1.6 millisecond delay or latency in PON is some research in progress to reduce this delay. Atul Gupta sir, if you may like to answer, sir. PON.
Yes, so that is very much there because PON is also a potential candidate for all the front haul segment, and there is already work going on, and I believe the later standards have reduced the delay also latency, and new schemes to address the latency issue, because latency essentially comes from the fact that the bandwidth needs to be allocated to the ONTs. It's not a continuous transmission. So that is very much there. Yeah, that's correct.
Thank you,
New
sir.
standards will address that.
Many participants are asking for PPT that we will share. That we will share afterwards. We will try to share it. Ashok Jha, sir, any other question? This question which I took on latency, it was from you only. If one person.
Okay, can you hear me?
Yes, sir, please.
Yeah, that is a thank you. It was a very good explanation from him that it is due to bandwidth allocation to the ONTs for which the delay occurs. So my subsequent question would be, does it mean that if we have a fixed wavelength, not wavelength, that bandwidth allocation already fixed, will that network be more speedier? Because we are depending on dynamic allocation. That is our purpose, that we cover more and more. But suppose I design a network in which there is no dynamic allocation, rather it is a fixed allocation, will it improve the latency? That is my subsequent question to you. Thank you.
Sir, I think in that case, it is not necessary that the latency will get improved. The reason being is that the whatever information has to be sent from ONT, still it needs to be stored for some period of time till the slot, even if it is a fixed slot, till that slot actually comes. So I think the solution lies in two things. One is to have sort of moving towards WDM PON, where a wavelength is assigned. And the other thing is that there is a faster allocation of slot to individual ONTs. So if the DBA algorithm gets improved, the allocation can be done much faster and the latency will get reduced. Having a fixed slot will make the latency more deterministic, but may not be necessarily smaller.
Thank you so much. Thank you.
Any other question? Please raise your hand. We will unmute from our side. So one question, Suhas Patil sir, he has asked in chat. Let me see. What is the initiative being taken by Indian Telecom Authority to promote in-house development of new era fiber optic cables and new technologies for breaking Shannon's limit? Please, any speaker who want to answer? He has written his question in chat. Suhas Patil. Nitiraj sir or another speaker, Mr. Anjani Kumar Vai sir, please, if you want to answer, sir.
I think Professor Tyagarajan mentioned that CGCRI. This is Atul Gupta from CDOT. CGCRI, yes, CSIR lab at Kolkata, they are already working on new fibers. I think he mentioned Sterlite also. Just yes. That is what I picked up from Professor Tyagarajan's lecture.
Thank you, sir. So I think we don't have any question. If you just, we can wait for another 1 minute or 2 minutes for questions if you have. Our speaker, eminent speakers are there, so you can ask any question. Otherwise, we may end the session. Okay.
Nitiraj, simply you have mentioned about XR optics being developed and deployed by Infinera. So what is it similar to the PON network where we divide and split the signal, or in the SR optics, different lambdas separately can be taken to the different directions?
So different lambdas can be taken to different direction, and other difference is basically since it is based on this Nyquist subcarrier, you can do the upgrade on the fly. Basically, if you want to increase the capacity from 25 to 50 to 75 to 100, that can be done on the fly.
So it is being deployed in your chipset, or it is in the process of research?
It is already deployed in our chipset. We have done multiple trials, and I think globally it is getting deployed in some of the customers.
So it will be great help on 5G or future coming 6G networks.
Yes, sir. That is the actually reason that we have come up with this kind of technology, and mainly for the backhaul requirement where there is a need for higher capacity with 5G.
Thanks.
So with this, we come to end of this workshop. I would like to thank our DG sir for his guidance, and again, our DDG sir, Sri Raju Sinha sir, who has been instrumental in conducting behind this workshop. And I would also thank all the participants and speaker who have come to this workshop and contributed a lot. So DG sir, if you allow, then we may close this meeting, sir.
Yes. We may close now. Thank you very much, everyone, for your contribution and participation. Thank you.
Now I am just ending the meeting, please. For any further queries, you may write these numbers. This is my and Sri Raju Sinha's sir numbers is there. So for further on email or phone number, whatever you want, available. Thank you.